And then if you remember on the right-hand side, we've kind of got more mission type stuff about orbits and night-day acquisitions and things like that. But then we transition through the science questions to the things we need to measure in order to answer the science questions, to the measurements we can actually make in order to retrieve that information we need to answer the science question, right? And then in the next column, we translated that into a bunch of instrument requirements. So this course is still really not on the engineering end of things. You're going to get to that in the next course, the 400 level course, which is just space mission design and analysis. But what I'm going to go through today is how we can use reflectance remote sensing to make some of these measurements that we need to answer some of these important science questions. And I'll be talking about this. We're going to do 2 sessions this week, and then next week I think we'll actually just sit down and get you looking at some real satellite data, and hopefully then that will make some of this become more real to you. So we're going to look at some satellite images of the Big Island, something that you'll probably be kind of familiar with. So, you know, when we were putting this thing together, I looked at all of the planetary science missions that have been launched since Sputnik. Hey. And you know, they carried largely, there are several instruments which all of these things are carrying, and that's not by mistake. We haven't really invented a new physics in the last 80 years. Most of the experiments that have been carried by this spacecraft, initially they were just particle counters. So some of you are working on that as part of your project, right? You have the Vices, and what's the other one called? Sorry.
Crepes.
Crepes, right? So these are both just particle counters. Is that correct? Right. So the earliest missions just went round and round the Earth, and they just counted when they intercepted a high energy particle. Right. We got more sophisticated. We learned most about what we know of the world around us by using our eyes. Right. Our eyes are remote sensing instruments. They are reflectance spectrometers. So we quickly started including cameras on these spacecraft. So you also saw the spectacular images of Mars and the Moon, and you can see some of them. You know, there's the Moon over there on the wall. And what we're doing there is just letting the sunlight shine onto the surface of a planet and then measuring the light that gets reflected back, right? So in exactly the same way that your camera works on your cell phone. Pretty soon we realized that looking in black and white isn't that useful. And then we started splitting the spectrum up into different colors so that we could do spectroscopy. Measuring the amount of light reflected at different wavelengths tells us something about the chemical composition thing that we're looking at. So pretty soon we started going from just black and white framing cameras to what people call multispectral cameras, right, where we're splitting the spectrum up using filters typically. As I'll describe in this class, the finer and finer you split the light up, the better and better you can perform this reflectance spectroscopy, and you can really start to fingerprint materials and distinguish not just clays from iron oxides, but different types of clay, which might have some special scientific significance. So when that happened, we stopped using filters and we started using things like diffraction gratings. Who in the class, are you all engineers? What are you? Astronomy, right. So you know all about spectroscopy, right? Engineers. So we've got astronomers and engineers. Okay, great. So we started doing what people call hyperspectral remote sensing. Right, again, reflectance remote sensing. What I'm going to cover in my section of this course is reflectance remote sensing and emission remote sensing. So either studying the amount of light that planets reflect and using that to work out something about their chemical composition, or using basically equivalent measurements of the amount of light that planets emit because they are warm, and using that information to also do some spectral fingerprinting and chemical fingerprinting from orbit. When we were putting the course together, you know, we looked at this thing, and people are increasingly particle counters, so gamma ray spectrometers was something that was quite big. A lot of missions have taken those because it tells you something. Reflectance spectroscopy, as I'll show next time, basically is probing the outermost electrons in an atom or a molecule, right? Whereas gamma ray spectroscopy, you can probe something closer to the nucleus, right? So Peter's spoken to you about gamma ray stuff already. Okay, so a lot of missions have carried gamma ray spectrometers. Tyro spoke to you last week before, or something like that, right? So increasingly people are carrying active remote sensing instruments on planetary missions, not so much from orbit yet, because there are significant power implications for active remote sensing from orbit once you go away from the sun, right? So planetary missions, unless you're going out to the outer solar system, they still rely on solar panels, right? Planetary missions, you know, the kind of things that Matt Damon was carrying around in The Martian, the radioisotope generators. NASA doesn't have a limitless supply of plutonium, right? They get it from the Department of Energy, and the Department of Energy get it from basically retiring the nuclear stockpile. So that is limited. So when you're kind of in the Mars type orbit and inside you're using solar panels, you're far from the sun, right? Which means you're limited in terms of your power. And techniques like Tyro was talking about are quite power hungry because it's like a flashlight. You're generating your own signal. So if you think about your cell phone, you can take pictures all day. As soon as you turn the lights off and you start taking pictures with the flash, you discharge your battery, right? Because the camera's running and you're also sending out this pulse of light, and there's a cost to that. Those are the main types of remote sensing that we're going to speak about in this course, right? So gamma ray spectroscopy, reflectance and emission remote sensing spectroscopy, and also the LiDAR. The LiDAR is very important now on the planetary rovers. So Tyro would have spoken to you. He's part of the Mars 2020 team, and they're using LIBS and Raman on the rovers to actually make chemical composition measurements of the surface of Mars. So we've chosen those three things. Those aren't the only type of experiments or instruments that have gone to do space science in the solar system, but they are the majority of what's going on. Right. So by the end of the course, you'll have a good feeling for the main instrumentation that we've taken out into the solar system to answer these science questions that NASA really cares about. I'm going to talk about reflectance remote sensing. So in my classes, I put one of these at the front. This is just like a narrative for what we're going to talk about. In a few weeks, when you've completely forgotten anything that I've said, if you want to refresh yourself on what we spoke about, if you just read that, it should give you the basic refresher of what the following slides are. Okay. There's no exam for this class, right? There's an assessment component, which is a presentation and things like that. Yeah. So in this class, you know, again, this might be elementary for some of you, but we'll go over it. I imagine Tyro spoke about spectroscopy and he did it probably at a kind of high level with some math and stuff like that, right? So I'm going to use pictures largely to describe similar things, but this is a different type of spectroscopy than the Raman spectroscopy that he's been talking about. So we'll just go through it with some pictures and some very elementary introduction. So we're going to talk about spectroscopy, how it works, and then the instruments that make these measurements. And one thing that I'm going to spend a lot of time about is talking about this thing called the remote sensing process, which is just the chain of events that has to take place in order for us to successfully make a reflectance remote sensing measurement from an orbit around the planet. And we'll just go through each of the links so you can appreciate something about all of the steps that are involved. And that's important when you come to the space mission design and your final capstone design class, right? You can't just build an instrument in isolation and ignore other parts of this chain, right? Because it won't work. So we'll talk about this. Mainly we're talking about, as I said, reflected sunlight. So I'm going to talk about passive remote sensing. So there are two types of remote sensing. One is passive, one is active. Passive means the instrument itself does not generate light, right? It just measures light generated by something else. And I'm going to say light, radiation, EMR, it's all kind of the same stuff. Right? Although strictly light is just a visible part of the spectrum. But passive remote sensing. So in this room right now, my eyes are passively remote sensing all of you, right? Light, photons from these lights are landing on you. Red photons and blue photons are being absorbed by whatever pigments dye the cotton in your shirt. Green photons are not being absorbed by whatever pigments dye the cotton in your shirt. They are therefore being reflected to my eye. Those photons are focused by my lens onto the back of my eye. The back of my eye, I have photoreceptors. I have these ones which are good for black and white, and then these tri-stimulus things which are good to separate red, green, and blue light. Only the green one is stimulated. That passes some electrons to my brain, and then my brain somehow interprets that as green, and I call it green. Right? But my eye isn't generating any light. Right? The light's generating the light, so it's passive. We'll talk about later in the semester thermal remote sensing. You are above 0 Kelvin, therefore you radiate light. I can design an instrument, kind of like the ones I'm going to talk about today, which measure emitted light. But again, it's passive. Right? Something else is generating the signal. Active remote sensing would be the LiDAR type stuff and the LIBS stuff that Tyro was talking about. and also microwave remote sensing, radar remote sensing, if anybody's ever seen any of those kind of data. Maybe I'll show you some images later in semester. Those are imaging techniques where the instrument itself generates the signal, right? And we shine the signal at the target, and then we measure how the properties of that signal get changed after interaction with the target, right? So that's exactly the same as using a flash on your phone, right? The phone generates the signal rather than just freeloading the signal of something else. So what we're mainly talking about is the sun, right? The sun is going to be the source of our signal that we're going to use for these measurements. And we're going to shine that sunlight on different targets on different planets. We're going to basically study how the composition of that sunlight gets changed via that interaction, and that's how we're going to work out mainly the chemical composition of the target of the Moon and the Mars and Mercury, etc., etc. We'll talk about this briefly in the next class, but the basics of spectroscopy. What's happening, why are certain photons absorbed and certain photons are not absorbed. We'll leave that till next time. The light that's reflected needs to be sampled. So this is this remote sensing process. So we're going to have to record the photons that get reflected back, right? And because usually scientists are interested in mapping stuff. So if you look at these images, they're mainly maps, right? They're interested not just in knowing how much light got reflected from a planet, but how much got reflected from that part of the planet and that part of the planet and that part of the planet, right? We work out how things work based on the spatial association of characteristics. So we need some way of sampling the light that comes back in a way that we can retrieve a map, right, or an image or a map of how much light got reflected from that point on Mars's surface and that point and that point and that point, right? So we've got to sample this light. We've got to collect it using some kind of telescope. We're interested in, as I said, color remote sensing or spectral remote sensing. So the light that gets bounced up from the surface and arrives at the telescope and gets focused onto the focal plane array, before it lands at the focal plane array, we have to split it into its different frequencies or wavelengths or colors, right? So we need some kind of spectrographic system. And then finally, we need this transducer, which is going to convert a flux of photons. You cannot count a photon, you can't measure a photon, but you can convert photons into something that you can measure. So the transducer or the focal plane array, the detector that's in the camera in your cell phone, converts photons into photoelectrons, right, with some kind of quantum efficiency, right? So we convert photons into electrons. And then we basically kind of count the electrons. We usually do that by allowing a charge to build up and then reading out the charge. And the charge is proportional to the amount of light that struck the front of the telescope, right? Satellites don't do very well communicating things like 2.41 electron volts, right? On the spacecraft, we have to digitize an analog signal, convert it from electron volts or current or volts into a digital representation, some kind of binary representation. The spacecraft stores that. When the spacecraft goes over a receiving station, it downlinks that information by modulating a carrier wave, zeros and ones, zeros and ones. And once we get that data down, as long as we haven't broken any links in this remote sensing chain, and we'll find out about this next week, I can give you a satellite remote sensing data set. You can load it up in a piece of software, and as long as that chain isn't broken, you'll be able to go in, pluck out a number for an area on the Big Island, and you'll be able to convert it into an estimate of the number of photons that got reflected from that patch of ground at each wavelength or frequency. Right. So that's what we're going to talk about today and next week. Does anybody have any higher level questions about this? No, should we just start? Okay. Okay, the eyes and the brain, a rudimentary spectrometer. So we won't spend too much time on this, but as I just described, we have light from passive remote sensing. We have light from a source. It lands on the T-shirt. The T-shirt reflects a certain amount of light. This is why you don't wear black when you're playing cricket, right? Cricketers, anybody familiar with that game? England, people wear white clothes, right? You're out in the sun all day, it's white, because you don't want to get too hot, right? You want to reflect as many photons as can, because if you absorb them, it gets converted to heat, and then you get too hot. So if we look at this, we have our brain which perceives the spatial and spectral variation of photons that get reflected from the things that are in our field of view, right? So if we just look at this one, sunlight comes in, and then let's normally say that's all frequencies of light. It's not quite, right? The sun emits a black body spectrum nearly, right? Not all frequencies arrive at the top of the Earth's atmosphere because the sun's atmosphere absorbs some of them, but most of them do. The Earth's atmosphere absorbs different frequencies of light, so not all of the light that lands at the top of Earth's atmosphere makes it down to the surface, but we'll just say it's a kind of complete spectrum. And that isn't useful to us, right? We said we want to split this light into different colours or frequencies. So light comes in, hits the t-shirt, gets bounced back to my eye, my brain processes it, and in some way I work out what the colour of the t-shirt is. Now, we use this colour theory, which is very different than paints. When you're messing around in class when you're a kid and you start mixing paints, right? This is a very different way of interpreting colour, and this is the way we're going to use it in the lab next week. But it's all in here. This isn't very complicated. So the way it works, if these photons come in, if the t-shirt is white to my eyes, that means that the t-shirt was reflecting red photons, green photons, and blue photons in about equal amounts, right? And high amounts. So in this color space, white means lots of light, right? And kind of equal amounts of light at different colors. Let's just say red, green, and blue. Right? We're just talking about visible light at the moment. If I look at a t-shirt which is yellow, nobody's wearing one. What that's telling me is that this t-shirt, the pigments that have been used to dye it, are very, very effective at absorbing blue photons. Right? If the t-shirt is really effective at absorbing blue photons, that means blue photons just get absorbed and converted to heat, and they're not available to be reflected to my eye. Right? However, the t-shirt isn't very good at absorbing green photons and red photons. So the green photons and red photons are reflected to my eye. And in this color system, green plus red equals yellow. So green plus red equals yellow. Right? So that's why a t-shirt is yellow to my eyes. Magenta, similar thing. This t-shirt is very, very, very good at absorbing green photons, but not very good at absorbing blue and red photons. If something isn't good at absorbing photons at a particular frequency, that means it's very good at reflecting photons at that frequency. Right? So I get reflected lots of blue photons and red photons, which when they arrive at my eye, red plus blue equals magenta, and then so on and so on. Right? So this is how we talk about colors in remote sensing and reflectance spectroscopy. Finally, if I was an idiot and I went out playing cricket in black, what that would be telling me was all these photons from the sun are striking the t-shirt, but again, the pigments that have been used to dye it mean that it's very, very good at absorbing blue, green, and red photons. Because it's very good at absorbing blue, green, and red, that means it's not very good at reflecting blue, green, and red. Right? Absorption and reflectance for opaque targets are just the inverse of one another. So if it's absorbing all the blue, green, and red, that means it isn't reflecting them. That means this thing is not reflecting much light at all, which is why it looks black to my eyes. So these are just simple rules about how we interpret colors in satellite remote sensing images. And you'll work on some of these next week. But this is as simple as it gets, right? So as in class next week, as long as you've got this with you, you'll be able to work out what we're talking about in terms of the differential absorption and reflectance of photons across the surface of the big eye. Okay. So how do we quantify this? We can make a plot just like this, and you'll be seeing reflectance remote sensing and emission remote sensing is just squiggle hell. It's just a life of squiggles and graphs like this, which are called spectral signatures, spectral emission signatures in the thermal infrared, or spectral reflectance signatures in the visible shortwave near infrared. People seen these before, the astronomers have seen loads of these things, right? So what do we have here? We just plot on this axis the wavelength of light, right, going from shorter to longer. So I'll just confine myself to kind of the visible part of the spectrum here. Wavelength of light measured in millions of a meter, so obviously we're in the metric system, the imperial system. And typically remote sensing, we typically use microns or nanometers. So people are familiar with these units, right? I mean, I'll show you some equations where you use meters, but typically we always convert to microns and nanometers simply because it's convenient to say a half, right? It's not convenient to say 10 to the minus 5, right? So we use microns, but sometimes people just convert that to nanometers, in which case that would be 500 nanometers, 600 nanometers, 700 nanometers. So in terms of this unit, microns and nanometers are really common in the planetary science community, simply because it's a convenient number. We're not raising it to a power. And as I said, so wavelength of light in meters, this is 10 to the minus 6, nanometer would be 10 to the minus 9. So that's all we're plotting here. On this axis, we're just going to plot the amount of light reflected by the object. And at the moment, we'll just say, all the way down here is the minimum amount of light that my eyes can detect. Right? My eyes can detect some minimum amount of light. You get up in the middle of the night, you need a drink, you can't see anything, and you're stumbling around. Right? The amount of light being reflected from objects is below the level that my eye can resolve. Up here, the maximum amount of light that our eyes can detect when I look at the sun, I'm saturating the detectors at the back of my eye, and my eye has maxed out in terms of the photons that it can measure. And this goes from low here to high here. And what we're going to plot here is just the spectrum. So the red t-shirt, if you remember what we said with the red t-shirt was, it's been dyed with pigments. It looks red because it's reflecting red photons. It's not reflecting green and blue photons, right? The chemicals in the pigments in the cotton are absorbing green and blue photons. So if I just plot that up, blue light, typically about 475 nanometers. If it's not reflecting much blue light, then the amount of light reflected by the object is very, very low. And I've just arbitrarily plotted it down here at the bottom. I've also said it's absorbing all the green photons. So I'm going to plot that here on this line. But I told you it was reflecting like a ton of red photons, and that's why it looks a vivid red. Right? So this doesn't look a pale, it's not that red, the glasses case, right? So that would be kind of a low intensity red. That's an intense red, right? So it's a very pure red. So I'm going to plot the amount of red light reflected, this wavelength, all the way up here. And then if I just draw those lines, I produce a spectrum, right? That's a reflectance spectrum of the light reflected by that red t-shirt. And what we're going to do in planetary remote sensing, what NASA pays hundreds of millions of dollars for, is designing instruments to make these measurements so we can make lots and lots of plots that look like this. More complicated than this, but just plots that look like this, right? Because this is the spectral fingerprint of the chemical composition of that t-shirt. And we'll talk in, as we go along, how we can invert that and basically use the shape of these curves to work out what elements and molecules are actually doing the absorbing. Because that's kind of smart remote sensing, right? If I can get a spectrum with peaks and troughs in it, and I don't know anything about it, but from first principles I can work out what molecules and ions are present in order to produce those absorptions, then I can do things like they did the other day when they discovered some fancy organic molecule on the surface of an exoplanet. Right? They did that by producing curves that look like this, and then looking which wavelengths were absorbed, because the chemical composition drives the absorption. Right. Just green, we won't go through all of this, but green here, so as I said, it's absorbing the green and absorbing the red and the blue photons. We plot that really low, reflecting the green photons, so the spectral reflectance curve of the green t-shirt looks like that. So red looks like that, green looks like that. And I'll give you an example. It'd be pretty easy for a machine to distinguish between those two curves, right? So we've moved from qualitative remote sensing of different colors, we're actually quantifying the amount of light reflected by these different things, right? So if you imagine we're scanning the surface of Mars, and we look at one area on the ground and the spectral reflectance signature is this, we look at another area on the ground and the spectral signature is this, we can easily write an algorithm that just distinguishes between those two things. Right, again, and that's what we do in planetary remote sensing. The curves are more complicated than this, but that's what they are. So I'm going to go through it all. Just talk about these at the end. So I said, the white t-shirt is very, very good at reflecting red, green, and blue photons. And because it's white, it's reflecting a lot of photons at all of those wavelengths. Right? The black t-shirt is very, very poor at reflecting red, green, and blue photons, which means it's very, very good at absorbing red, green, and blue photons, which means I get a flat line down here. So for a white t-shirt, I get a flat line up here, the spectrum. For a black t-shirt, this is the spectrum down here. Gray is a midpoint between these two things, right? So if you see gray, that's just telling you that the amount of light absorbed, reflected by the t-shirt is about equal in the blue, green, and red wavelengths, and about the same, but the intensity of light reflected is less than the white case and higher than the black case. Right?
We had previously kind of gone over the bell curve of visible color and light, and I was wondering on the bell curve it had like different intensities for different colors. So if you wanted for us to perceive white, would you have to have like I don't know which color it was, but one color be more intense in that sense, or is it if they are of equal intensity but very high intensity, it'll still be white?
So this is a normalized variable, right? So the curve you saw was a Planck curve, right? It's kind of bell curve. Looks more bell curved if you plot it on a log scale, right? But that's the amount of light. That's the amount of light in a derived SI unit. So you probably had something like watts per meter squared per steradian per micron on the y-axis versus wavelength. And it looked like a bell curve, and you're right. Way more light is emitted by the sun at the visible red wavelengths than at the visible blue wavelengths. Right? The way we produce these curves is by normalizing it out such that we go to a dimensionless variable, which is just the scaled amount of light. And we'll talk about that in a couple of classes. I'll just show you how to do that. Right? But it's a good question. So this is it. So bring this to class next week. When you're looking at a satellite image, as long you can look at a pixel on the surface of Mars and it's magenta, right? So it's pink. The first question you ask is, well, okay, if that's pink and I'm looking at reflected light, that's telling me that I'm getting a lot of signal in. At the moment, let's just say the red band and the blue band, right, to make pink. So I see a pink pixel in a remote sensing image of Mars. That's telling me that whatever is on the ground is reflecting a lot of light encoded as red light and blue light. Right? But whatever is in that pixel is absorbing the wavelength which I'm encoding in green light. The next question you ask is, which wavelengths am I displaying in red, green, and blue? So these are just display colors, right? For as long as we have eyes that have evolved in the way our eyes have, we will just see in the visible part of the spectrum. But in remote sensing, we can make instruments or eyes which measure the amount of light reflected at wavelengths that are invisible to us. Okay, so the infrared, X-ray, UV, shortwave infrared. But we still have to encode it in colors that our eyes can see if we're going to interpret and analyze images. So the first thing you do is say, what's the color of the pixel? How do I make that color? That's telling me that I have a strong signal in the red band and the blue band, but not in the green band. Or whatever wavelength in the green band is being strongly absorbed by whatever stuff is on the ground at that point on the surface of Mars. The next thing you say is, well, which wavelengths am I displaying in red, green, and blue? And on the basis of that, you can relate it back to one of these curves and say, well, if I'm seeing magenta, then that's telling me that I'm getting strong absorption about, in this case, 550 nanometers. And then you can go to your tables and say what kind of mineral absorbs light at 550 nanometers, and then you can show people how smart you are and say there's iron oxide on the surface of Mars. So we'll take you through a load of examples that show you how this works. But if you understand this, and I'm sure the astronomers do, if you understand this is how you interpret these images, and don't lose this. Bring it to class next week, because we're going to be looking at images and you'll be asked to interpret colors. So as a planetary example, people have seen this stuff before, I'm sure. Rusty rocks look red because, why does it look red? Whatever is there is absorbing blue and green photons, but not red photons, right? And that's why we see red. That's why red photons are reflected to our eyes. So this is on the surface of Mars. This is the real Sojourner. This is Matt Damon carrying the fake Sojourner around on the surface of Mars. But we know Mars kind of looks red, right? The red planet. So why does it look red? We can stop at it's red, right? So just from this, you can say, well, whatever's on the surface of Mars is absorbing blue, visible blue and green photons and reflecting red photons, right? And that's why it looks kind of red. But this isn't a pure red like that, is it? It's more of it's not even quite that red. It's kind of an orangey red, right? So, what we're seeing here, if we go back here, how would you make an orangey red, do you think? So this is red, right, where we have complete absorption of blue and green photons, gives me this vivid red. But what I'm seeing on the surface of Mars is not a vivid red, right? It's kind of an orangey red. In the Roy G. Biv rainbow spectrum, what kind of primary color is close to orange?
Yellow.
Yellow, right. So how do I make a yellow?
So you absorb a little bit less green.
Right. I need to add some green photons into the mix to balance out the red photons, thus producing a red which is more like an orange. Right? So here are a few points, and I've just plotted up the spectra here. So this is a reflectance curve, right? So here we've gone to, instead of saying amount of light, we're still on wavelength, right? Still in the visible part of the spectrum. I've converted to reflectance, so this is this normalized thing that we'll talk about end of this class or next class or something. This is a spectral reflectance curve. Reflectance is a dimensionless variable that just goes between 0 and 1. Sometimes it's expressed as 0 to 100%, right? Where 100 is the most and 0 is the minimum. So just 3 spots, the grey, the blue, and the green. So does it make sense? This is the visible blue part of the spectrum, this is the visible green part of the spectrum, and this is kind of the visible red part of the spectrum, right? So the curve that I just showed you that would produce a completely red t-shirt is flat from blue to green, and then it goes up to red. And we said we have to add some green photons to make a vivid red look like a kind of orange, because we need a bit of this yellow, right? And that makes sense looking at this, right? This is blue, this is red, and then here we have green reflectance. Right? We have some green photons. If this spectral signature went from here to here and then here, this would be yellow. Right? But by adding that little bit of green reflectance, or reflecting some green photons from this dirt, we get more of an orange color than a red color. And then, this is a spectral signature measured over on Mauna Kea. We have basically red rocks over at the summit of Mauna Kea, right? The dirt is red. People make t-shirts out of red dirt. And the reason these look the same is because they are the same. So, does anybody know what rock Hawaii is basically made of? The whole thing, virtually.
Basalt.
Basalt, right? It's a rock type called basalt. Basalt contains, essentially has to contain 2 minerals. It contains a mineral called plagioclase, which is the most common. I'm going to throw out some geological names because I know you're all engineers and some of you are like star-type scientists. But as I said, NASA does science for a reason. So if you're going to do this kind of thing, you have to be vaguely familiar with something about the science that people do. So there are a couple of minerals that have to occur in a basalt. One of them is a thing called plagioclase, which is the most common mineral in the Earth's crust. And the other is a thing called pyroxene, right? It can also contain, occasionally, or sometimes contain olivine. So people have been to the green sand beach over on the Big Island. So those are olivine crystals, right? Those are green crystals. Basalt sometimes contains olivine, but it always contains pyroxene and plagioclase. Pyroxene is what people call a ferromagnesian mineral. What do the ferro and magnesium stand for?
Iron and magnesium.
Iron and magnesium, right? So the iron rusts in the presence of oxygen and it turns red. Right? So that's why you get these red soils at the summit of Mauna Kea. Mars is composed mostly of basalt at the surface of the planet as well. And in an early part of Mars's history, it's thought that the atmosphere was wet and oxygenated, and it also rusted the basalt to produce red rocks. So this is the spectral signature of rusty rocks, but what we're really saying is we're detecting the presence of ferromagnesian minerals that have been exposed to an oxidizing environment. So we've gone from just saying red and orange and blue and green to actually some kind of chemical fingerprinting of minerals on the surface of another planet. People good? Right? Is this interesting anymore? Okay, the cool thing is we don't just have to stick to the colors that we can see with our eyes. As I said, our eyes, for good reason, have evolved to just be sensitive to visible wavelengths of light. And the definition on that varies, but it's something like between about 0.4 and about 0.69 microns is from the visible blue to the visible red. Once we go below that, we're in the ultraviolet, and once we go beyond that, we start going into the near infrared, shortwave infrared, and then we go out to thermal infrared wavelengths, and more. But we can build spectrometers. We're just building mechanical eyes, right? The instruments that are on the satellites that we're going to send into space, and next class, the class after, you're going to design a satellite that's going to carry an instrument to do something. We can design that reflectance spectrometer to make measurements of the light reflected at wavelengths that are invisible to our eyes, right? Which is the cool thing, because otherwise we'd just be able to distinguish things which we can distinguish, which we can perceive. So as an example, this is again an image acquired by the Curiosity rover on the surface of Mars, and then this is host rock, and then these are veins. So when people say host rock, that just means the rock, and then a vein might be like an ore deposit. So you form the rock, and then as a secondary process, new minerals or rocks are introduced, and they form, in this case, veins. This is interesting because this is telling us about a geological process on the surface of Mars. Right. Most of the Earth's gold is locked up in its core, right, and we can't get to it. However, we do mine gold, and people do look for ore deposits of gold and extract it and turn it into kind of expensive jewelry. The fact that we have those veins is telling us basically that these ore deposits, and any ore applies to any ore on the Earth's surface, what's happening is the host rock is formed, which is usually just a volcanic rock like basalt or the kind of volcanic rocks you get in the Andes. And then rain falls on that rock, and the rain percolates down through the rock, and it hits hot rock, and it reacts with the hot rock, and it leaches out elements like gold. And then you get a convective, the water's then hot, it's hot and element laden. It rises, right, because it's buoyant, and it rises up through the Earth's crust. And then as it cools, it precipitates in cracks in the rock. And that's how we form an ore deposit, largely. I mean, there are variations on that. But these veins are kind of like those things, right? We've had some process which has taken elements from the rock, leached it, and then concentrated it in these veins. Right, in the same way that we concentrate gold and platinum and copper in certain points on the Earth's crust. So that's telling us a process took place. Right? If you think about it, that's telling me, on the Earth, that's telling me that we have water. If the Earth was stripped of its atmosphere and nobody knew anything about it, and from space I could find localized gold deposits from remote sensing measurements, that would tell me that that planet had at one point had a moist atmosphere, which allowed water to cycle through the upper crust. Again, that's just geology stuff. You're designing, NASA doesn't build cool stuff. It tries to answer science questions. Most of them are geological, evolution of planets type stuff. But this is telling me something interesting. So if I can distinguish the veins from the host rock, that might be a New York Times headline, right? Okay. Now let's just look here. So in this visible part of the spectrum, so I've gone to nanometers here, but I've put wavelengths beneath it. If we just look in this part of the spectrum, the grey box, then the shape of these curves is kind of the same for the veins and the host rock, right? There is a subtle difference in brightness, but the shape of those spectra is the same. So what I'm looking at is either a dull red, a dull orange, or a kind of slightly less dull orange, right? Because again, the shape is very similar. Low reflectance in the visible blue, high reflectance in the visible red, with a little bit in the middle, so these green photons that are giving me orange rather than red. But I can design this instrument to make measurements at wavelengths that my eyes are insensitive to. And if we look out at these wavelengths, you'll see that there's a sharp decrease in reflectance between about 900 and 1,000 nanometers for the veins, with a much more shallow decrease in reflectance in the host rock. People see that is steeper than that, right? So that's how I can most effectively distinguish between the veins and the host rock, right? And to do that, I just had to design an instrument which made measurements of the photons reflected out here in the near infrared. Now the physical cause of this is basically the presence of hydrated minerals or trapped water in the crystalline lattice of the vein material, but not the host rock material. Right? And I've just plotted up a bunch of things here: sulfate, water ice. If we just look at water here, you'll see as I get into this part of the spectrum, water does this thing here, right? I get this little trough. So this is a reflectance curve, and remember, this is something to drill into your head. In reflectance curves, the interesting stuff is not happening in the peaks, it's happening in the troughs. Right? We measure the peaks because we're actually measuring the photons that get bounced back to our eyes. But for an opaque target, reflectance and absorption are inverse to each other. So a trough tells me that an absorption was taking place. As we'll talk about in next time, the absorption is taking place because the ions, the atoms, the molecules that comprise this thing are very, very efficient at absorbing photons at this wavelength, but not this wavelength. Right? And the wavelength at which different materials absorb photons is Z number dependent. It depends on the atoms and the molecules and the ions that comprise the thing that we're shining the light on. So water ice has this trough, about 1,000 nanometers. This is actually an overtone of a fundamental absorption which takes place kind of out here somewhere. But this is diagnostic of water, and if we look in all of these hydrated minerals, we'll see that we have a little trough in each and every one of them. So this little trough is telling me something about the presence of water in the crystalline layers. And I can resolve that in this measurement. So we'll show some more examples, but that's the advantage of designing mechanical eyes to do reflectance remote sensing. We're not just confined to the visible part of the spectrum. Most of the things we're interested in studying exhibit characteristic absorption features at wavelengths that are invisible to our eyes. We just have to make an instrument that can resolve that difference in reflectance. Right. Now here's just an example of a quick algorithm that could be used to distinguish the veins from the host rock. So this is really old. I'm sure they use machine learning, whatever that is, these days. But this is a technique called run length encoding. And those old fingerprinting type things that you see, they use something basically like this. So again, what's this curve called?
Spectra?
Spectra, spectral reflectance curve, right? I've got reflectance on this axis and I've got wavelength on this axis, right? And then if I imagine, I go into my image of Mars and I pluck out this reflectance curve. So this is the reflectance curve I actually get from the data, right? And I plot it up. And then, and people have done this, I go to a library of all the possible spectra of all the possible minerals that exist in the Earth, right, and the universe. And I say, okay, which one of those things is my Mars spectrum most like? This is how I spectrally fingerprint something. So, the way I do this is, I take my measured spectrum and I take a library spectrum and I just iterate these library spectra through, right? I just go from 0 to 1 million. And I choose a window of wavelengths, so region of interest. And then for both of these things, so let's just first take the library binary code. I take the average reflectance over the window. And then I say, is the measured spectra above or below the average? So in this case, at that wavelength, is the solid blue line above or below the mean over that window? Easy question.
Below.
Below, right? So if it's below, I put a 0. Right? This wavelength, it's below, I put another 0. This wavelength, it's below, I put another 0. At this wavelength, it goes above, so I put a 1. Right? 1, 1, 1, 1, 1, 1, 1. It dips beneath, I put a 0 and a 0. It goes back above, and I put a 1. I then repeat for this window over here. Okay. I then go to the spectrum I measured from a pixel on Mars, and I just repeat the same process. For the same window, I compute the mean, and I just go, is it above or below? Is it above or below? Is it above or below for these two windows? Zeros and ones, zeros and ones, and then I just compute the match. So if it was a 0, and I have to keep these wavelengths in order, right, obviously. If I get 2 zeros, it's a 1. If I get 2 ones, it's a 1. If I get a 0 and a 1, then it's a 0, right? I didn't get a match. And then at the end of this process, I just count up the zeros and ones, divide by the number, and I get a match of 17 over 24, which is 71%. Right. So in that case, I basically said there's a 71% match between my library spectrum and the spectrum I got from the image of Mars. Now the cool thing about that is, the library spectrum, somebody took a mineral or a rock, and they ground it up into a powder, and they made very precise measurements of its spectral reflectance in the lab, and that's how I get the library spectrum. But the key thing is they know what it is, right? Because they know the mineral. So at that point, I've gone from this kind of weird wiggly curve I got from an image of Mars to actual knowledge of what the actual mineral is. Right? So in planetary science, people spent a ton of time doing this. So the universe is composed of certain things, right? Most of it's hydrogen and helium, and then the rest of it is just a trace contaminant. Luckily for us, right, this trace contaminant exists. But in terms of the formation of planets, there's only so many things that a planet can be formed from. Planets are kind of big, so you can't form a planet from platinum, because the stellar nurseries, in the time taken for our solar system to exist, have not produced enough platinum to make planets. They produce plenty of oxygen, plenty of silicon, plenty of iron, all those kind of things that make the rocks. So people have gone out and said, okay, let's look at all the minerals that occur on Earth, and let's make these reflectance curves, and let's put them in a spectral library, so that in the future, people that make these measurements from planetary probes can just take their measurements, compare them with our library, and in that way work out what the surface composition of Pluto is. Right? We're never going to go to Pluto, but we have spectral reflectance measurements of Pluto. We think we know what the ices on the surface of Pluto are made of. We can simulate those ices and rocks, make measurements in the library, in the lab, and then fingerprint what's on the surface of Pluto using this kind of technique. So that's what a lot of remote sensing is. So there's this dumb remote sensing, well, it's orange, it's red, it's green, it's yellow, it's pink, which means I've got a bit of red and a bit of blue. But the real power comes from taking our spectra and inverting them to get back to some knowledge of the chemical composition of the thing we're measuring. Any issues? Do people see how this is so important? So what I'm mainly going to talk about is remote sensing from an orbital perspective. Right. So Tyro's spoken about landers and rovers, and they're great. So this is Curiosity. This is from the Mastcam thing. So this is the surface of Mars, and then all I plotted here are a few reflectance curves. Again, same thing for red, green, black, and the blue dots on the surface of Mars. Right. So this thing carried a grinding tool. And it did that for a couple of reasons, and I'll talk about this towards the end of the class. What do you notice about the color of this and the color of this?
It's less oxidized, probably.
Right. So this is not red, and this is red. Right. So this is less oxidized. Why would it be less oxidized?
It was underground.
Because it wasn't exposed to the atmosphere of Mars. Right. So oxidation is a weathering thing. So we make rocks. And then when rocks are made, they equilibrate, crystals equilibrate under conditions of high temperature and pressure. Right? They're made real deep. So the rocks that made the Big Island probably originated at about 70 or 100 kilometers depth, where the mantle temperature is about 1500 degrees C. Right? So that's when we make the minerals. We transmit them up to the surface, and we dump them on the Earth's surface as a lava flow. Those rocks are less stable at low temperature, low pressure conditions on the Earth's surface. And changes can take place, and we call those changes weathering. Right? Oxidation is a weathering process. So this is what the surface of Mars looked like, basalt. This is what the powder looks like if you just grind basalt up and take it from beneath the surface. Right? So the rover can do that. If we look at this, we get this nice red signature where we have high red reflectance, lower green, and not so much blue. But for the powder, we get a kind of flat spectra. So this is the spectra of actual basalt. This is the spectra of oxidized basalt. And then I just plotted a few others, right? So we've got this point and this point. Now, these are all kind of different, but you can see they all have this feature, right? This ramp up from the visible blue to the visible red. So rovers are great, but what's the problem with these rovers? How big are planets? Big. I mean, they're kind of big. I mean, here are some. These are all. This is a single image of Mastcam, right? So I haven't put a scale on this, but this is pretty small, right? And you all know these rovers don't truck around at great speed, right? So rovers don't really allow us to sample much of a planet's surface, right? You just don't get much data. And as an example of that, if I went to a real geologist and said, I picked up half a dozen rocks from around the surface of the Earth, and I think I know how the planet works, they would laugh in my face. Right? To really work out how a planet works, you need to make measurements all over the planet. Right? And then we can look for spatial associations of different rock types, which might point to the operation of geological processes on a planetary scale. So rovers are great, and for some things they're essential, but you get a much different perspective when you go to an orbit around a planet. Right, so this is why we don't just send rovers out into the solar system. apart from them being very expensive and the challenges of landing them on planetary surfaces, we really need a planetary perspective. So this is the surface of Mercury, mapped in the visible near-infrared part of the spectrum. So these are false colors. So you've seen Mercury and it looks like that, right? It's just gray. So that's a Clementine-ish image of the moon. Mercury just looks gray, right, to our eyes. You see I've got lots of blues and yellows in this image, right? That's because this is what's called a false color image, and we'll talk about that next week, which is displaying colors that are invisible to my eyes in false colors so that my eyes, A, can see them, and B, it highlights certain things. So how do I make blue?
Blue photo.
It's an easy one.
Yeah.
So just go through the process. Blue means this is a reflectance image.
So it absorbs green.
Right, so whatever was on the surface of Mars here, right? But here's the thing. Let's first say, how do I make blue? Blue is a presence of blue and an absence of green and red. Right? In remote sensing images, when you look at them, as I said, you will load up a red, green, blue color composite, right? Where you'll have one band in red, one band in green, one band in blue. Right? At this point, you don't know what the bands are. You don't know the actual frequencies or wavelengths. But if you see a blue pixel, you can say, well, I'm getting strong signal in the blue band and weak signal in the green and the red band. Right? And that's all I can say at this point. Is it a pure blue or a washed out blue? It's kind of a pure blue, right? That's kind of quite a vivid blue. So this is telling me that I'm getting a strong signal in the blue band and a kind of weak signal in both of the other bands, the red and the green. The next question is, which wavelengths am I displaying in red, green, and blue? Right? I could be displaying any wavelength in those colors. If I then, at that point, I can say, well, I'm displaying the amount of light reflected at 1.1 microns in the blue channel, and the amount of light reflected at 0.7 microns in the green channel, and 0.4 microns in the red channel. Right? At that point, I can say, well, this is blue, but it's blue because whatever is on the ground on the surface of Mercury is reflecting lots of photons of 1.1 microns, but not many photons of 0.7 and 0.4 microns. And then I can start thinking, what materials characteristically absorb and reflect at those wavelengths in that manner. Right? So here are just a few spectra of the surface of Mercury. So from this area here, the crater, low reflectance, geologists use, planetary geologists like drawing maps, and some of the words they use can seem pretty childish, but you can't go on the ground, right? So often you'll see geological units divided up into things like crater, low reflectance material, because that's really all they know about it, right? It's from the crater, but it's of low reflectance and it has a low spectra. This is a thing which planetary geologists like, which is intensity over this value F, which is kind of like reflectance. It's another normalized value. Then we have the crater center, and then we have the crater wall. But you can see the spectral signature of the low reflectance, the wall, and the center is all different from each other. Right? Those are measurements that I couldn't make from a rover, right? Because I'd have to drive that rover all over the place. Not only would I not be able to make it from a rover, I might be able to measure this on one crater, but I wouldn't be able to measure it on all of the craters on Mercury, and therefore I wouldn't know if the crater I was studying was some weird crater or if it was the norm, right? Because sometimes we're interested in weird stuff, but really, nature likes bell curves to a certain extent. Right? So what we're really interested in is dominant processes that shape planets. So the ability to sample the entire surface of Mercury and produce spectra like that for every single point on the surface is the power of this kind of reflectance from memory. Right. Now, for the astronomers, people are studying exoplanets, and you get like a fractional measurement, right? And it's usually mixed with the star, and you've got to use all sorts of weird stuff to back it out. So for planetary remote sensing, we'd have to do that all. I mean, I can't remember the resolution of these data, but I'm pretty sure it was like tens of meters per pixel. Okay, so that's just some background to why we do planetary remote sensing and some of the key concepts. I'm going to spend the rest of the class talking about this thing, which is the remote sensing process. So this bears on what I've just spoken about, but also a lot of the design concepts that you might implement in your design project when you get to the final class. So this is for the reflectance remote sensing process. So this is a chain of events. So it's going to start on the surface of Mars. I care about measuring something about Mars. NASA's given us $1 billion to do it. So this is my signal, right? This is the sun. Sunlight is going to shine on the surface of Mars. There are some wrinkles here. On the Earth, what is between me and the sun? Atmosphere, right? So if I were on the Earth, then the light that came from the sun would first have to pass through the Earth's atmosphere, and its composition would change as it passed through the atmosphere. Mars has a very tenuous atmosphere. It does have an atmosphere, right? So we do have to include the atmospheric effect. Shuai Li, who's one of my faculty in HIGP, he says he exclusively studies airless bodies because there's no atmospheric effect to correct for, right? Because the atmosphere is a pain in the arse. If I'm studying the surface of Mars, the surface doesn't change anything, right? It's set in stone. These weathering and erosional processes, which are driven by basically the presence of moisture and an atmosphere, don't take place on Mars. The only active stuff on Mars is really those winds and those dust devils, and maybe there's some volcanic activity occasionally. But the atmosphere changes quickly. So if I'm interested in studying the surface of a planet, the atmosphere is a confounding effect. But let's imagine there's no atmosphere, or I don't care about it. So sunlight is going to strike the surface of Mars. I'm going to introduce a unit. This is our signal, and with any signal we have a unit. And the unit we're going to use is this thing called spectral irradiance. I'll talk about this in the next class on Thursday. Irradiance is the amount of light striking a target. Okay, so solar irradiance is the amount of sunlight arriving at the top of Earth's atmosphere. So spectral irradiance denoted this, and then the units are watts per meter squared per micron. So again, this is a derived SI unit. If we think about what this is, watt, what's 1 watt?
Joule per second.
1 joule per second, right? What's a joule? Unit of energy, right? You flip over a candy bar and it tells you how many joules of energy you're going to get by eating it. So we have joules per second per meter squared per area on the ground per micron, because I'm not interested in all of the light. I'm just interested in the visible green light or the visible blue light or the near infrared light, right? So what this unit is telling me is the energy in joules per second per meter squared per micron. And I can convert that into the number of photons with just some easy dividing out. And photons, remember, a photon is a little packet of energy, carries an amount of energy. The spectral irradiance arrives at the surface of Mars, and then what leaves the surface of Mars is something called spectral radiance, so this is the unit we're going to use. We denote it L lambda, and it has units of watts per meter squared per steradian per micron. Okay. Anybody know what steradian is? Doesn't matter, we'll talk about it next week, right? This is a term that is useful. Sorry, I get that.
Do you want to just pop it up?
Actually, yeah, sure, that'd be good. Thank you. This is a term which is which derives from a assumption we make in remote sensing, which simplifies our lives greatly. We'll talk about that next time. But people see it's basically a similar thing, right? Energy comes in, energy goes out, right? And this is what's available to measure to me. This is the signal. What comes in gets changed into what comes out via its interaction with the surface of Mars. And this is where all those characteristic absorptions are taking place, right? Photons are all wavelengths that come in and striking the surface, but because of the chemical composition of what's here, photons at some wavelengths are being absorbed, right? If it's absorbed, that means it is not reflected, right? If it's not absorbed, then it is reflected, and it's available for me to measure. So this is why, as I said before, the interesting things happen in the troughs in these curves, right? Because that's the Z number dependent, chemical dependent absorption. But spectral radiance comes out. So this is our signal, right? So this is great. Now we have to harvest the signal. So how do we do that from space? We have a satellite, right? And on it we have our telescope. People are familiar with things called pixels, right? Pixels, picture element. Pixel is just like a display thing. It doesn't really mean that much. We design the optics on the telescope such that we can say that pixel is equivalent to an area on the surface of Mars, which is 10 meters by 10 meters. Right? The important thing isn't the pixel, it's the area of ground sampled within a pixel. right? Because again, we want to make a map, right? We don't want a single pixel for the surface of Mars. We want to divide it up and make a map of spectral radiance as a function of location, right? So the way we're going to do that is by sampling the surface of Mars. And we sample the surface of Mars most effectively by putting the spacecraft in an orbit, right? And usually for these kind of planets, we use some kind of near polar orbit, right? Apart from Uranus, our planets all kind of rotate like that. Am I getting that right? Anti-clockwise. Right, they all rotate like that. Uranus kind of rotates on its side because people think it got smashed by a large planetary embryo, which kind of flipped it over. But the planets rotate like that. So if I put a spacecraft in an orbit which is fixed in inertial space and it's just going round and round and the planet rotates beneath me, then in that way I can sample the entire surface of the planet, right, without needing any propulsion on the spacecraft at all. This is how we commonly describe the geometry of this process. So the spacecraft's moving in this direction, this is the surface of the planet, and the planet's rotating beneath it. The limits of the solid lines here are what we call the field of view of the instrument, right? So the field of view is how much of the planet can I see at any one time, right? So my field of view is that, right? I can't see very well what's in that room, and I can't see at all what's over there, but this is my field of view, right? If I did that, then I just cut my field of view in half, right? Because I can no longer see what's over here. If I wanted to increase my field of view again to what it was, what would I do?
Step.
No, I will not do that. What would I do?
Oh, step.
Okay, that's a good answer. Yeah, we'll talk about that soon. I could step back, but if I step back, my resolution decreases, right? Because I can't resolve far away stuff as well as I can. Now I'm good, now I'm not good, but how can I get that back?
You turn your
I can scan, right? I can just scan the camera backwards and forwards in order to recover that field of view. So this is how most of these spacecraft work, right? A lot of them, they have some kind of scanning mechanism because, and I'll show you some simple calculations. The focal plane array that you use is usually kind of small. It's difficult to make large focal plane arrays that have really good performance across the entire wafer. So what you do is you make a smaller focal plane array, which is really, really good and really well characterized and calibrated. And you scan it across the surface of the planet over a wider field of view to give yourself this larger area coverage. That's called whisk broom scanning. Another kind of scanning is push broom, which is where you don't scan at all. You just plow that focal plane array across the surface of the planet. Can people think of the advantages, disadvantages of both of those things? The advantage of the whisk broom is you get a bigger field of view, which is great because you get more data more quickly, right? What's the disadvantage of a whisk broom scanning approach?
Does it like affect, is there like parallax in the image that?
If you go too far off axis, yeah, you can get some weird stuff going on, especially if you have a planet with an atmosphere, because then the atmospheric path length is much greater off axis. From a spacecraft design point of view.
Requires more energy.
Right, I mean you have to power it, right?
You have to keep it stable too, and like
Right,
looking
so
at
a rocking mirror, the way these things work is you just have a mirror which you rock, which you oscillate really, really quickly, and that deflects light from different points of the ground into the telescope. So you don't point the telescope, they just put a scanning mirror in front of the telescope which bounces light from over there into the telescope and then over there into the telescope. But you've got this mirror that's rocking backwards and forwards, and this mirror can be like this big. And it's oscillating really, really quickly.
Oh, is it like more fragile and possible to break?
Right. Right, so all of these things that you said, it's more massive, it needs more power. If the mirror stopped working, the mission kind of just ended, right? So planetary science missions, they're really scared of single point failures, right, and moving parts in general. So that's the flip side, you know, the scanning approach gives you a greater field of view, but you have this scanning mirror. Which can break on small spacecraft, can introduce a jitter, right? Because this thing's oscillating. It's not doing that, right? Because the spacecraft's moving at 7 kilometers a second or whatever it is. It's really rocking backwards and forwards really, really quickly. So it can export a jitter to the rest of the spacecraft, right? Which is just like if somebody was tapping me on the head really, really quickly, my vision would be blurred, right? There are also things like, you know, if the coatings of the mirrors change, then it it changes that chain. That's a break in that link in the chain. But you'll see this in planetary missions, right? Different approaches. There are pros and cons, and there are costs associated with any of these things. So on the mission, on the science traceability matrix, the scientists might say, well, I need a big wide field of view. And then it's like, well, okay, we don't have a focal plane array that can give us that in the push-broom techniques, and now we need a scanning mirror. Some engineer has to build it and make sure it works and make sure it's reliable and make sure it does this for 5 years, which is the mission lifetime without breaking. Somebody's got to pay for it, right? Because maybe you haven't designed this mirror before and you've got to pay a bunch of people to get it going. But anyway, that's just, I'm going to point to examples about how things that come from the left-hand side of the science traceability matrix can impact you over on the right-hand side of the science traceability matrix. So we're scanning backwards and forwards, and then you see these little checkers in here that I've drawn. These are the pixels, right? So that's my field of view, but within it, I can resolve light reflected from small parcels within the field of view, and that's what we're going to call the pixel. And I'll just show you a quick example about how we would define that. But as the spacecraft's moving in this direction, what I'm doing is I'm saying, well, I'm going to scan over there, and then this is like an electrical engineering timing thing, right? The mirror doesn't go scan, stop, scan, stop, scan, stop, scan, stop. It just scans continuously. And it's just bouncing light into the telescope continuously. But what we need is somebody to write an algorithm that says, okay, I've sampled light from that patch of the ground, and then 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 that patch of the ground, until I've moved forward 1 pixel, right? And then I go back, and I just repeat that. Right, so I've got to finish 1 line before I move 1 line. Otherwise, I'm mixing my lines and my columns. But this is just a timing thing. I'm just bouncing light in via this scanning mirror. I go, rup, rup. And in that way, I make a 2-dimensional map of the amount of spectral radiance reflected from every single 10 square meter patch of the surface of Mars. Right. Okay? So that's how I produce an image. I may not need the scanning thing, but if I don't have the scanning thing, I probably sacrifice field of view. On a surface like Mars, maybe not that important. On Mercury, not that important. If I expect things to change quickly on the surface of a planet, then it's important that I acquire data as frequently as possible. And in that case, I might really want a wide field of view because that gives me the greatest coverage in the shortest period of time. So all this light's come up and I've sampled it. I've sampled spectral radiance from this checkerboard on the ground, right? So I've done most of the job. Spectral radiance is basically all the light that came up. We're going to make spectroscopic light, so I now have to split the light into its different frequencies or colors or wavelengths, right? So I need some kind of spectrograph, which is going to take the light that comes in and split it into different colors. Right? And I've just drawn visible colors here, but these can be invisible colors. These can be the infrared, ultraviolet, shortwave infrared, right? I've drawn a prism here. I'll show you in a couple of slides. Prisms are used. I mean, prisms are actually pretty decent. But people tend to use now increasingly things called diffraction gratings, which I'm sure the astronomers have heard out, and maybe even the engineers. And there are a couple of other techniques. People used to use filters, now it's increasingly gratings because we want this higher spectral resolution. So I have a spectrograph which splits the light into its different frequencies. And in that way, I now have a measurement of the amount of blue light, blue photons if you like, blue light, red light, green light, in the same unit. So I haven't changed the unit. But I've split it up into its different frequencies. I did point out, so this thing, once I've collected it, there's a telescope which focuses it, right? The next thing I have to do is I have a stream of photons, and I can't measure these things, right? So I have to use my transducer, my detector, to convert something I care about into something I can actually record and measure and record, right? So that's the job of the focal plane array. So you have an FPA in the back of your phone, right? I'll show you just some pictures of it. The focal plane array includes a light-sensitive wafer on the top, which is chemically tuned to be responsive to photons of some wavelengths but not others, right? And then beneath it, you have some readout electronics, right? Which allow you to accumulate photons, convert them to photoelectrons, accumulate a charge of photoelectrons, and then read out that charge such that the charge you read out is proportional to the amount of spectral radiance that was reflected from each one of these pixels. Right. And these things, this is an example of a way these detectors work, but a lot of them work kind of similarly. So we have some semiconductor material, right? We have a valence band and a conduction band. This is just a picture, there's no gap between this stuff, right? You just take a crystal and then you add impurities to the crystal such that you can easily dislodge electrons at some wave photon energies but not other photon energies. Remember, the photons that we're measuring are coming out. A visible blue photon has much more energy than a visible red photon, right? Because the blue is short wavelength, high frequency, and the red is long wavelength, low frequency, right? A blue photon carries more energy into the joules than a red photon. When I shine blue and red photons on this material, the blue photon might contain enough energy to dislodge an electron from its position in the lattice. Right? If it dislodges an electron from its kind of nominal position in the lattice, then that electron is now free in that semiconductor material. In the presence of a bias voltage, this is the battery, right? I just flow electrons around this thing, so bias is just it's constantly running. I have current going through here. In the presence of this bias voltage, the electron I dislodge can be swept up in that current. Right? People see this? Here, I just have a resistor, a reference resistor, and then I just measure either the voltage drop across the resistor or the changing current through the resistor. And in that way, if I shine a ton of blue photons on this material, I will get a ton of photoelectrons being dislodged that can be moved. A ton of photoelectrons will be swept up in the bias current, and that will be reflected in my measurement over here. So effectively, the detector is working like just a variac, a variable resistor, right? I shine blue photons on it, which have enough energy to dislodge electrons from the semiconductor material. They get swept up, and then I just measure that changing current across this reference resistor. Now the key thing is here, I mentioned blue photons have high energy, red photons have low energy, right? The key thing here is the red photons don't have enough energy to dislodge an electron from the valence band to the conduction band. So this is Einstein's photoelectric effect, right? Doesn't matter how many red photons I shine on this thing, they do not have enough energy to dislodge an electron from its position in the lattice of the semiconductor, right? So that means when I shine red photons on here, I don't get any change in current, right? Because I'm not generating any photoelectrons. So this band cap can be tuned for different wavelengths, right? We can make focal plane arrays which are sensitive to visible light, shortwave infrared light, long-wave infrared light, right? Just by tuning the chemistry of the focal plane array semiconductor material. Did people know how these things work before? Okay, people happy with that? Right? So these things are really expensive, right? So I paid the better part $2 million for the JPL to make me one of these things, right? Because there's a really low yield. As I said, you're taking the semiconductor and then you're doping it with another element which either has an excess or a deficit of electrons, right? And you add the dopant, and if you add too much of the dopant, it isn't responsive to the wavelength that you care about. Right? So it's kind of like a chemistry thing. The way they do this is they take the silicon wafer and they put it in a chamber and they heat it up so that the lattice expands. And then you introduce the dopant as a vapor, and those ions kind of nuzzle into the structure, and then you cool it down. And you do this, and then you test it, and we didn't get it right. So then they have to repeat the whole process. So it's a bit like the old flat screen TVs. 20 years ago they were really expensive because the yield was really low. It's very similar to these things. But this is a kind of science traceability matrix thing. Ideally you are not developing a new focal plane array, because if you are, it's really expensive. So if a scientist wants a new focal plane array, they better have a good reason for it. So we're good on this. What we're doing is we're taking spectral radiance, which comes from the surface of the planet, we're sampling it, we're splitting it up into its different color components, and then for each one of those we're going to convert photons into photoelectrons, and we're going to generate some output signal which might be a voltage change or a current. Right. Now this is what that looks like. Remember, the mirror is just going backwards and forwards and the spacecraft's going forward, so we have a continuous signal, right? The way these things work is in the time we're looking at that patch of ground over here, so this pixel, we define what's called an integration time. So your camera has an integration time. Old cameras used to have exposure times, right? The integration time is how long am I going to sample light from that patch of ground? And it might be just a couple of hundred microseconds. Right? The way it works is, okay, my integration time is a couple of hundred microseconds, which means I'm going to look at that patch of ground for that period of time, then that patch of ground for that period of time, then that patch of ground for that period of time. In a couple of hundred microseconds, as I said, the focal plane array has a photosensitive wafer on the top, some kind of semiconductor. But that just generates photoelectrons, right? This stuff, this is all electronics, right? So this is what they call the ROIC, or the readout integrated circuit. People heard of that before, right? So you've got the photosensitive wafer on the top, and it's split up into pixels, right? But in each pixel, you have to read out the photoelectrons from that pixel, right? So how do you do that? You take the ROIC, which is basically for every pixel in the photosensitive wafer, you have an integrated circuit, which people used to call a silicon chip, which in old-fashioned world is a transistor and a capacitor. So a transistor is a gate, and a capacitor is a bucket into which we flood electrons. Right? So beneath each pixel of this photosensitive wafer, we have a capacitor and transistor. Now, this integration time comes in by saying, okay, I'm going to allow charge to accumulate. I'm going to open the gate, the transistor, and I'm going to allow photoelectrons to fill that capacitor for 200 microseconds. And then I'm going to close the gate. Right? And that's how I sample the light, and that's how your phone works to a certain extent. Right? And then I'm going to read out how many electrons I collected during that integration time. And that's how we convert an incident continuous flux of photons into a discrete estimate of the photoelectrons generated for each pixel in the image. Okay, with this gate bucket type thing. And then the gate and the bucket, the chip is bonded to the focal plane array using a low melting temperature metal like indium. So they're just like conductive bumps that couple each pixel in the photosensitive array to the corresponding gate bucket in the ROIC. I'll show you a picture. People okay? So we've got these discrete measurements now. So this is one integration time, this is another integration time, this is another integration time, this is another integration time. So this is current or voltage. I've shown voltage here. But this is how much light was sampled from that point, that point, that point, that point, that point. So you can see this is a sampling timing issue, right? When the spacecraft's going forward and the mirror's rocking and you read out all this stuff. This isn't a convenient number to store, right? 3.24 volts isn't a convenient number to store or transmit. So we just digitize it using some kind of transform, right? We just convert a voltage to a binary representation of that voltage. So we go from volts to zeros and ones. Now at this point we store those zeros and ones, and then the spacecraft transmit that data to the ground. And next week in class you're going to be given data that just look like this. Right. So here, digital representation of the output voltage in dN. So dN is digital number, sometimes DC, digital count. You're going to get, it's not CD, we're just going to put it somewhere for you to download. You're going to get a satellite image of the Big Island, or a couple, and it's going to be multiple wavelengths. It's going to be a map of the Big Island, right? So just like this. And it's going to be a load of pixels in it. And for each pixel corresponds to a patch of ground on the Big Island, which is about 30 meters by 30 meters. And for each patch of ground, we've made measurements at multiple wavelengths, right? Multiple different colors. So you're going to get multiple different files of the Big Island for different wavelengths. And in each pixel, you're going to get a number that looks like that, 358 115. And that's the digital number. And then we're going to show you how to put these images together such that you get an image on the screen. I mentioned that this is a chain of events. Right. So I've just written this down in words. So we care about the reflectance of the surface of Mars, right? That's the thing that's encoding this chemical fingerprinting information, which we're going to use to tell us something about planetary processes on the surface of that particular planet, right? So reflectance is what we care about. Reflectance is a function of some condition that we care about. Here. Reflectance is a function of some condition we care about. But we're not going to measure reflectance initially. What we're going to measure is this quantity spectral radiance. And I'll show you how that's related to reflectance, right? That's the thing that's actually we're going to measure. So we're going to assume that the radiance we measure is a function of the reflectance, which it is. And I'll show you how it's functionally related. We're then going to assume that as we go through this chain of events, this delta voltage or delta current that we measure is a function of the change in radiance sampled by the telescope as the spacecraft is going overhead, right? And it is, as long as we get this whole design process right. Okay. So now, we're going to assume that the dN that comes out of this is a function of the change in voltage or current, right? And it is, because this is pretty simple. So now we've gone from the radiance that we measure being a function of something that we care about to the dN in the image being a function of some condition that we care about, right? Because we haven't broken that chain in any way. If you break that chain, then the dN in the data that you get on the ground may not be relatable back to this quantity, right? Which is the real thing that we care about. So we'll talk about this more in detail. A lot of this is calibration of the instrument, for example. So astronomers know a lot about calibration, right, and how important it is. And at the end of it, you're going to go into a satellite image and you're going to be able to reproduce spectra that look like this from a satellite image. And when you're doing that and you're marveling at how smart you are, just remember that this is the process that allowed you to do all that work. So I've what time are we on? Midday already. What time do you usually go?
1.
Okay. Do you want to break for a little while and then we'll... Yeah, sorry about that. But people are good on this?
Yeah.
This is how reflectance remote sensing of almost every planet we've ever studied works. Right? So if you understand this, then you understand how it works. Okay. So why don't we come back in 10 minutes at 10 past 12 and we'll just finish up.
So if you're having to deal with the atmosphere with the spectral irradiance, you also have to deal with it on the return, like spectral radiance. So you have to take into account both when you're measuring.
Right. Yeah. So, and there are a couple of ways of doing it. If I put something, so I've got a measurement there where the light came from the sun, went down through the Martian atmosphere. It got changed between the sun and the surface, and then it went back up through the Martian atmosphere and it got changed again, right? So it's been changed 3 times, but the only one I care about is the one in the middle. One way, a simple way of doing that people occasionally use, is what if I put a target on the surface of Mars, which I know is perfectly reflects all wavelengths equally, right? And I measure the spectral radiance from the thing I care about and from that target. Now in that case, the target, the light from the sun came down, got changed by the atmosphere. When it hit the target, it didn't get changed at all, right? And then I look at the light from the target, from the white thing, right? Got bounced back up in it, and that light got changed again. And then I compare that with the light that came from the rocks I care about. There was 3 events, right? The light came from the sun, got changed by the atmosphere, got changed by the target, got changed by the atmosphere. For the white standard, the light got changed by the atmosphere, did not get changed by the target, but got changed by the atmosphere in the same way. So I can just subtract one from the other, and the residual will be the change that I care about. So that's one way, and I'll show an example of that. We'll take a camera out and do some stuff, but that's one way of normalizing for the effect of the atmosphere. You know, we can't put white tarps on the surface of Mars. You know, that's one way we do it on the Earth. We can just go out and put reflectance standards on the ground. On the Earth, people are also using variant targets. So if you go to some of these evaporite lakes in the Andes, they kind of look white and they don't change with time. And you can look at what you care about, look at the evaporite lake, subtract one from the other, and basically isolate the atmospheric effect. Yeah, can't do it on Mars, can't do it for most of the Earth. So we won't go through this in much detail, but the data I'll give you next week. Another way we can do it is use a radiative transfer approach, where we take the photons, we compute the photons coming from the sun and how many arrive at the top of Earth's atmosphere. And then we build a model of Earth's atmosphere, all the aerosols and particulates and all the gases. And we just use a physics-based approach to work out how many get absorbed as the light passes from the top of the atmosphere to the Earth's surface at each wavelength. And then we flip that around and work out how many get absorbed as the light goes back to the spacecraft. And that's how we characterize the atmospheric effect.
Complicated for sure. If,
Complicated, and there's an error, right? I mean, it's not that there's no error.
and then because of the atmosphere, if it's a particular like heavy atmosphere, there no matter what, there's going to be some wavelengths that you'll probably miss out on because they're like absorbed stuff.
So, if you think about Venus, think about any measurement, right? Any measurement is signal versus noise, right? And you want to maximize signal against noise. And usually to isolate signal, you do some correction for noise, right? If the correction for noise is 5% of your signal, then a large error in your noise collection doesn't translate into huge uncertainty in the things you care about. But if you imagine that your noise is 95% of the signal, right? That's not a situation you want to be in, right? Because then a small error on your noise correction is basically your entire signal. So if you imagine the case on Venus, Venus has a really dense atmosphere. There are wavelengths, most of the wavelengths in this part of the spectrum, the reflected part of the spectrum, are completely pointless to even try and explore on the surface of Venus, because you can't calculate out the effect of the atmosphere, because it's just too high a percentage of the signal. There are some narrow transmission bands in the Venusian atmosphere which there's a mission called Veritas, which kind of NASA funded and kind of cancelled, but they're looking at the surface reflectance of Venus because they want to map evolved volcanic rocks versus non-evolved volcanic rocks. So if you like, some people have suggested there are rocks on the surface of Venus which are like the Andes, and then there are rocks on the surface of Venus which are like the ones we have here in Hawaii. You can only make rocks like the ones you have in the Andes if a planet contains a good amount of water. So to find those rocks will be evidence that Venus was indeed wet at a previous point in its history. There's a very narrow wave band that you can see the surface of Venus that would allow people to distinguish Andean-type rocks from Hawaiian-type rocks.
I think Professor Engler had talked about that last semester a little bit.
Yeah. But if you're on the moon, there's no atmosphere, right? So it's really easy. If you're on the Mercury, there's no atmosphere. But that's part of that. That's part of that science traceability matrix thing. So if you're at a planet with an atmosphere and you're saying, if I make these measurements, I can definitely answer this science question. If you have a model of the atmosphere that you need to use in order to answer the question, then that model has to be good, right? That model can't be crap, because then the reviewer would say, well, your model of the atmosphere is not good, so how are you going to answer the question? Astronomers, have you done this before, this kind of stuff?
Not this in depth.
Okay. I mean, the detectors, there are lots of different types of detectors, but they kind of work like that.
We just gone through talking about detectors in,
Yeah.
Well, if you,
and the concepts are almost.
Yeah.
I mean, so it's easy to understand after we just have a lecture yesterday on that.
but for the
Talking
people
about
who've never heard about this before, does that kind of make sense?
Yeah.
I mean, they're not dissimilar to solar panels on your roof. I mean, if you have photovoltaic on the roof of your house, you are harvesting photons, converting to photoelectrons. And there's probably something at your house that gives you a plot that shows power generation from your plots. It's digitizing a continuous analog signal, converting it to something that you can plot. That thing at the end is timing thing. It's a continuous flux of photons that gets converted to a continuous flux of photoelectrons. But in the presence of a bias voltage, you can measure across a reference resistor. Then it's this timing thing, which is related to the integration time. If you think about it, I'm going to get an image where I have a top left and I have a lower right. And that can't be garbled, otherwise it isn't a map. Right? So you've got to get all the timing right such that I know which pixel was pixel 00 and which pixel was pixel 2054 versus 346. Otherwise I can't produce an image, I've just got a stream of numbers.
Can you explain the red, green, blue?
Yep.
colors again?
So, if you remember I said we get to here, and this is white light, right? This is spectral radiance of all the colours that the atmosphere transmits. And it comes here, and then I've got to split it, right? Because I want to produce a plot that looks like this, where I say the amount of reflectance at this wavelength and this wavelength and this wavelength. So I split it up using some method. Could be prism, could be filters, could be a grating. Now, I might have different filters in front of a bunch of detectors. But going back to that blue-red photon example, blue photon carries a lot of energy. Right? If the band gap is kind of broad, right, the band gap is really how much energy do I need to kick an electron loose from its position in the lattice, such that it becomes free, and then can be swept up in its bias voltage. Now, we draw it like a picture, but it isn't a picture. Right? I mean, the photosensitive material is a crystal, right? And you have electrons. And it's not a metal, right? So these electrons aren't floating around all the time, they're held in the lattice. But photons with a certain amount of energy can free these electrons, right, if they have enough energy. So if I want to measure a photon which has a shorter wavelength or a higher energy, but not a photon that has a longer wavelength but a lower energy, I would make this band gap wider, right? Because then it requires more energy to free an electron. So I can tune that because I know I can tune the energy required to free an electron because this is a thing that's made. And I know the energy of a blue photon, a green photon, and a red photon. So this can be tuned in the design, in the manufacture of the device. But say I want to tune blue photons, and I'm going to make the energy, the band gaps, wide enough that only blue photons can free an electron. Right. When blue photons hit here, they have just enough energy to kick an electron across the band gap, but really just free it from the lattice. And then I sweep it up, and then the more blue photons that fall on here, the greater the change in voltage or current across this reference resistor. Right? So that would be a lot of light. If you like, a large current would be a lot of light. Right? And say that's current, that would be a point up here, not down here. Right? Here, not down here. Lots of light, not much light. So increasing amounts of light, and remember that here to here to here is here to here to here, right? Increasing amounts of light, decrease. So this pixel here, the fourth one, was slightly darker than this pixel here, right? Because I got less current, because I generated fewer photoelectrons, right? So this is a trace of the amount of light that got reflected from each patch on the ground. It's just in shitty units, right? Volts is not a good unit. So what I'm going to do is just digitize this using just a transfer function. And convert it into zeros and ones. And then that's going to be converted into this thing, which is called a digital number. And when you're on the ground, you get a file which has, it's a georeference file. And imagine these are just empty boxes which correspond to geographic points on the surface of Mars.
Pixels.
Yeah, pixels. And in each pixel, I get a digital number. And each digital number is proportional to the signal strength, which is proportional to the amount of spectral radiance that got reflected back from that point on the surface of the planet. Right? And in these multispectral images, I have one map for each wavelength in the spectrum. Right? So the data I'm going to show you next week, we have one spacecraft called Landsat, I think we're looking at Landsat 7 data. That measures 8 spectral channels between 0.4 and 2.5 microns. Right? So I would get 8 measurements. I'm going to show you the surface of Hawaii Island sampled using another spacecraft, which makes 220 spectral measurements over the same. So for Landsat, I would have 8 of these maps. For this other spacecraft, I would have 224 of these maps. And if you imagine, I produce a spectrum by this pixel, and this pixel are at different wavelengths, but for the same geographic point on the surface of the planet, right? I've staggered them so you can see that they're co-registered in space. So I can just drill down through here, and if I was to plot that as a spectrum, in the red wavelength it would be 3, in the green one it would be 58.
So it just corresponds with how much.
This digital number is how much light is proportional, and just look at that, you know, the digital number is proportional to the amount of light that got reflected from the surface of the planet.
Got it.
We all back. 10 past, right? Okay, so just an image of how we build. So this is an example from the Earth. So this is a spacecraft called Aqua, NASA's Aqua spacecraft, and there's a sensor called MODIS. So this is what the orbits look like in 2 dimensions, right? So this spacecraft is in a near-polar sun-synchronous orbit. So it's about 700 kilometers, and it's inclined at about 98 degrees to the equator. So it just goes down, round, and round. So the planet's rotating, and this is the orbit just going round and round in inertial space. What you see there is the field of view. So you see that strip of images? That's the field of view of MODIS. So that's this whole thing. That's what MODIS can see at any one time when it's going over the surface of the planet. Within that image, MODIS divides it up into about 2,000 pixels in the across-track direction. So the pixel is green, which is the ground instantaneous field of view, or instantaneous field of view, and the blue is the field of view. But just relate this picture to that and this. Right? So this is how we build up a map of a planet from a spacecraft that's orbiting in a fixed ring in inertial space. Right? Spacecraft goes round, 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 the planet rotates beneath it, and in that way we build up coverage for the entire surface of the planet. Happy? There are some planetary issues at play here, again related to the science traceability matrix. So as a quick calculation, does anybody have a calculator or anything with them? Okay, so how many minutes are in a day? An Earth day, 24 hours.
60.
14.
So we've got 24 times 60, right, which is that. Do people know what the, I mean, you can work this out, but do people know what the typical period of an orbit is around the Earth? How long does it take for a spacecraft in Earth orbit to go around once if it's in a low Earth orbit? And, yeah, I mean, you can work it out, it's like 90 minutes. It's about 90 minutes to go around once. Right. So in a day, how many orbits do I get?
16.
About 16.
Yeah.
Right. So I've drawn this here, but this isn't a, we'll come back to this. Imagine if my field of view is, and this is an example from a real spacecraft. Imagine if my field of view is 185 kilometers, right, across. So every time the spacecraft comes down, it sees 185 kilometers, right? In one day, how much of the Earth, how much ground does it cover at the Earth's equator? 16 times 185 is what?
2,960.
2,000?
900.
3,000.
Yeah,
So we've got 3,000 right in a day. So my spacecraft that has a field of view of 185 kilometers in one day across 16 orbits samples, because the planet's rotating beneath it, right? Samples 185 times 16, which is about 3,000 kilometers. What's the radius of the Earth?
13,000 kilometers.
That's kind of the diameter. But
Oh, cut that in half.
6,700, roughly, right, the radius of the Earth. Circumference of a circle would be that times,
2 times
right, okay. So what's the circumference of the Earth at the equator?
2 times 5, about 3 times 7. 20.
40,000, roughly, right? So the Earth's surface at the equator is about 40,000 kilometers. In one day, a spacecraft that has a field of view of 185 kilometers only allows me to sample 3,000 of that, right? So how many days does it take me to sample the entire surface area of the Earth at the equator?
At least 14.
Right. So what we call that is the temporal revisit of the spacecraft. Right? if I'm on the Earth and I've got a spacecraft which is in that kind of orbit and the field of view is 185 kilometers, it takes me about 16 days before I completely fill in the equator, right, and give me global coverage. Okay. How can I increase my coverage rate or decrease the amount of time it takes me to fill in the equator?
Could increase your field of view.
Increase my field of view, right? If I double my field of view, I halve the amount of time, right? If I double my field of view, I might just have gone from one of these push broom sensors to one of these whisk broom sensors, which maybe people don't like, right? There was another thing that you had earlier. I can go higher, right? Or I could use a lower resolution telescope, right? But again, there's a penalty there, right? Because the scientists might want really small pixels, and I've just said, you know, the scientist says, well, I want 16 days, but I want really small pixels, so I can't do at least one of those things. Another thing I can do is add another spacecraft in a different orbital plane, right? But that's twice as much money. So on a planet like the Earth, this doesn't crop up too much as an issue. Well, on a planet like the Earth, things change dynamically. On the Earth, people are interested in studying the weather, changes in vegetation patterns, ocean currents, volcanoes, stuff like that. So you need high temporal resolution, right? If things are changing dynamically, you need to sample their temporal change in order to understand them, right? So there might be something that's driving you to a high temporal resolution, which as a mission designer, you have to accommodate, right? If I'm mapping the surface of Mercury, nothing changes, right? So on one level, it doesn't matter how long it takes me. If it takes me 5 years of the entire mission, that's okay, right? One example where this was an issue was the Veritas mission, so this Venus mission. So Veritas is going to carry a radar instrument, one of these active remote sensing instruments. It's going to pulse down microwave energy. It's going to measure the round trip, distance equals rate times time. And it's going to measure the small phase offset. It's going to go over one day, over volcanoes, and part of the mission is to detect volcanic activity on Venus. So it's going to go over a volcano and it's going to send a wave train down, get it back, and say, okay, this is the number of integer waveforms plus the phase offset of a fractional wave in terms of distance between the spacecraft and the volcano surface. Right? They do this on Earth all the time, and I'll show you some pictures. On Earth, they do that over Kilauea, then they go over again 2 weeks later and they make exactly the same measurement. If the surface of the volcano has expanded, then the surface will be closer, and that fractional phase difference will be less, right? Because the round trip time was less, because the ground has moved towards the spacecraft. So that might happen before an eruption. During an eruption, when the lava vacates the volcano, then the ground might subside, and the ground would move away from the spacecraft, right? In that case, I'd get an extra distance between the antenna and the ground surface. So this is a technique called interferometry, radar interferometry. The Veritas mission is going to carry an interferometer. It's going to go over volcanoes on Venus, and it's going to make this ranging measurement and say, how close are you to me? And then that doesn't do it, right? It has to measure the same volcano again, right, to see if any change took place. Venus rotates once every 243 days, right? So what that means on Venus is you can't have a one-year mission. So this is going back to the science traceability measures and all that sort of stuff. You've got a science question on the left-hand side, which is we want to know if Venus is volcanically active. Okay, how are you going to do that? There's a bunch of ways you could do it. One way is to see are the volcanoes deforming, right? Okay, great. That's the best way. We're going to design a radar instrument. We're going to make interferometric measurements. How long does the mission need to last? 6 years, because we can't just go over once. You know, one swallow doesn't make a summer, right? So you go over once, and you go over again 243 days later, and maybe nothing happened. Okay, the mission ends, and you just failed, and you don't have anything interesting to say, right? You've got to make that measurement over several years, right, in order to guarantee that you will generate a result. So that's just one example where this kind of orbital stuff on a planetary body impacted mission design. Right? Most planets don't change really dynamically, so we don't need an image every 16 days. But there may be science examples where to answer the science question is driving you to a particular orbital design because you have to make measurements with a particular frequency. So we'll come back to that later, but I'm just going to talk about 4 resolutions quickly. So you hear these all the time, you've probably heard them already. resolution number one, spatial resolution. So everybody kind of knows what this is. What's the size of the patch of ground that you sample the light from? So people say, what's the amount of detail I can discriminate from the image? If I have two closely spaced point sources of light, can I tell I have 2 point sources of light, or are they blurred into 1 point source? That's like a typical astronomy type definition. Think about it as this. What's the area in ground that I sample spectral radiance from? Right? Is it 10 meters? Is it 100 meters? Is it a kilometer? That's really what we're talking about. Some examples here, over on the big island of the Cacao Desert. Here's an image of that cone measured at 4 meter spatial resolution, and then here's the same patch of ground measured by a different spacecraft at 30 meter resolution. Right? So which image would you prefer? If you were doing geology work in the Cacao Desert, which of those images on the right would you prefer? This one, right? Because there's not a whole lot of information in that one, right? I mean, it's measuring the same stuff. It's measuring the amount of light reflected from the ground at a bunch of different wavelengths, which in this case were all visible. But the spatial detail and the spatial relationships in that we can derive from this image are much more useful than those that we can derive from this image, right? Spatial resolution is higher, spatial resolution is lower. So scientists always want higher spatial resolution, right? Everybody does. Everyone wants more and better. Your phone, how many gigapixels you get out of those things now. Question from an engineering perspective is, do you need it? So the scientist says, oh yeah, I need 0.5 meter pixels to do my science. Well, okay, and I'll show you on the next slide now. I need a gigantic telescope in order to give you that resolution, right? And this telescope's massive. And we can't even make mirrors this big, so it's going to cost a fortune. Do you really need 0.5 meter pixels? Right, so this is the science traceability matrix thing. The scientist has to defend these things, because any decision has implications huge implications with respect to cost. Okay? So they have to defend it on the basis of published work that they need 0.5 meter data. Also, there are knock-on effects. If you imagine this, if I decrease this to 15 meters, going back to that last example, in each pixel I have a digital number, right? And imagine it's an 8-bit digital number. To store that number, I need 8 bits, zeros and ones, right? So per pixel, the data volume I have to store on the spacecraft is 8 bits per pixel. Right? If I go to 15 meters from 30 meters, I now have 4 pixels for every 1 pixel. Right? So what just happened to the data volume I have to store on the spacecraft?
Quadruple.
It just quadrupled. Right? So again, if you're the computer person or the electrical engineer on this spacecraft, that just gave you a real headache. Right? Not only that, you now have to downlink to the Earth 4 times as much data as you did before. Right? So again, I'll point this stuff out as we go through, but every time a scientist makes a decision, they have to justify it because it just did what we just did, which gave us a telescope we can't possibly build or a data rate that we can't possibly achieve. But that's what it is in terms of science. So just a picture that shows you how you come up with this kind of numbers. So these are going to be numbers that you see in science traceability matrices. So just that you know how we got there. These are just some numbers for the LROC narrow angle camera, so Lunar Reconnaissance Orbiter. So the key numbers are, we have the ground, right? And we have this thing, the ground instantaneous field of view, which is the pixel, right? The area of the pixel on the ground expressed in meters, 10 meters, 20 meters, or whatever. This is nadir, which is the point directly beneath the spacecraft. We have our telescope, our optical thing, and then we have our detector, because remember the detector is that the pixel, this photosensitive pixel which is above the ROIC, which actually makes the measurement. Right? And beneath it we have the gate and the bucket. So, the detector has a certain size, right? So in this case it's 7 microns. Don't ask me why. Things like that are usually legacy. So detector sizes usually go, if you take 15, you cut it in half, you get 7. If you take 24, you cut it in half and get 12. No scientist ever says, oh, well, I've done this calculation over here, and I need a focal plane array that has detectors of 13.45 microns on side. Because now somebody's got to design a brand new focal plane array. So usually what you do is you take the focal plane array that you can get from Lockheed Martin or JPL, and you change the optics to give you the resolution you need. You never decide on that and then have a new focal plane array built. So key numbers, we have the detector element, we have the optics. The optics have a diameter, right? So is it a big telescope or is it a small telescope? And that basically determines how many photons you capture, right? The larger the diameter, so we have these huge space telescopes, right? They're trying to detect tiny numbers of photons coming from stars, and you need a big telescope to acquire enough photons to give you a decent signal to noise ratio, right? So diameter is just the size of the telescope. The focal length is the magnification, which is how small that detector is when you project it through the telescope onto the ground, right? So the focal length is the magnification, and that's a design thing, right? And that's the distance between the center of the optics and the focal plane array. The other variable is height, right? So as we said before, I can take the same telescope, and if I go further away from the target, the same angle extends to a larger area on the surface of the planet, and my spatial resolution just got worse, right? Because I moved further away. So if we just work through this example, F number is a number that you see in optics quite a lot. So that's just the ratio of the focal length to the diameter of the optics. And F over D in this case for this camera was 3.59. We can have lower focal numbers than that. We can have higher focal numbers, F numbers than that. If I make this thing large, right? So this is just the ratio of two things. So if I make that small, I'm reducing the diameter of the optic, right? Which gives me a smaller pixel size on the ground. That also means it's harder to garner photons because I just reduced D, right? Which means that my diameter is smaller, which means I collect fewer photons in a given period of time. People would call that slow optic, right? Slow because it's slow for me to connect enough photons to actually make a valid measurement. Conversely, I can make this number larger. In that case, I have a fast optic. But it trades off in terms of the spatial resolution. So first thing I can do is work out the focal number, the F number, 3.5. I can then work out this thing called the angular instantaneous field of view, which is just the ratio of the width of the detector to the focal length, and I get this number in radians or microradians. So the instantaneous field of view is this angle, right? So that's a number you see quite often because it's independent of range, right? The IFOV is just a function of that versus that, right? And we express it in radians. The ground instantaneous field of view is if I take that angle and I extrapolate it from the spacecraft to the surface of the planet, how does it grow, and then when it hits the planet, how big is that area? Right? And that's quoted in meters. So for this telescope, we had ground instantaneous field of view, or a pixel size of 0.5 meter for the LROC narrow camera. So if a scientist comes to you and says, well, I need twice as good as that, then you can just see from this the kind of things that you have to change to achieve that. This is an image that was acquired from that camera of the Apollo 15 landing site. Here, the ground instantaneous field of view imaged by this camera was like 26 centimeters. But I've just showed you that the design yields a ground instantaneous field of view of 50 centimeters. So how could I achieve 26 centimeters if my optical design is 50 centimeters?
Get closer.
Right, so that's what they did. In the final stages of this mission, they just remove some energy from the orbit, decrease the orbital altitude to about half of that, and got some higher resolution data before the mission ended, when the spacecraft crashed into the surface of the moon. People don't usually do that, right? But do people see, if I want to change this number, this is the number the scientist gives you, so you'll see this in the science traceability matrix. To answer my science question, I need 0.5 meter data. And then you've got to start translating that into, wow, what does that mean in terms of focal length? What does that mean in terms of F number? What does that mean in terms of detector size? What does that mean in terms of altitude? On planets with no atmospheres, you can get kind of close to the surface. On planets with atmospheres, you cannot get close to the surface, so decreasing the range is not an option, because that's going to drastically decrease the orbital lifetime. People good on spatial resolution? So we've just spoken something about the first step, spectral resolution, splitting the light into its different components. Right. So we need a spectrograph. This is you are not. if you get into this, you'll have to know this. I've just shown you a few things and shown you some basic relationships. There are several ways you can do this. You can use a prism, right? And prisms are pretty good. They're just a bit big. So I've put all the relevant things in here, but basically we have two index of refraction boundaries, one at one side of the prism, one at the other side of the prism. The incident ray comes in, we get refraction here with respect to the normal, it transfers across, we get refraction here, we get the emerging ray. Now if this is visible blue light, I can put a detector here and I can measure the amount of visible blue light, right? I just have to work out what these angles are and then build the focal plane array that puts the detector in the right place. With a prism, the key thing here is that the refractive index, which is n in here, so n of the prism material itself, for different glasses is a function of wavelength, right? So depending on which wavelengths I want to separate, I can use a different glass to give me more angular separation at some wavelengths than others, just by choosing a different glass, right? And because n varies as a function of wavelength, the angle of the emerging ray will bend for different wavelengths of light, and then all I have to do is put a detector to measure each emerging wave. Okay? That's how I could use a prism. And I've just shown visible wavelengths, but there are also glasses which give angular separation for longer wave infrared measurements as well. So we use a prism. You can also use filters, right? So this is common, you use them on your camera. There are two types of filters. There's an absorption filter, which is basically just you take a transmissive medium and then you dope it with chemicals which absorb light at wavelengths that you don't want to pass. Right? So this is just, you get like orange transparent paper or red transparent paper, and that's how those things are working. Right? So that's pretty easy. They're not that precise, and the problem with those things is they're absorbing the photons you don't care about, right? So if I absorb photons, what happens to my temperature?
Cool.
Right, I'm going to warm up. So those absorption filters aren't that great because they heat up, right, because you're absorbing light. The other type of filter that people use is a thing called an interference filter or a dichroic filter, where you take a piece of glass and then you deposit on top of it thin films, right, and you tune the thickness of those films such that the wavelengths of light you don't care about destructively interfere within the films and don't get passed through the filter. Right. So that's another way that you can design filters. And those things are more expensive, but they're more precise. And if you remember, I was showing you, we're interested in the amount of light between this wavelength and this wavelength. So we need some precision in terms of how much light we're emitting and how much light we're measuring. So filters work great. And typically in a two-dimensional focal plane array, the way they'll do it is they'll have a butcher's block arrangement of filters, where if you've got, say, imagine you've got 10 pixels in the in-track direction, 10 rows of pixels, you'll have a filter for one wavelength on the first row, a different wavelength on the second row, a different wavelength on the third row, etc., etc. And that's a way that you can generate multispectral data by just putting filters directly on top of the focal plane. Problem with that is you can't have 200 filters, right? So you remember I said we want to move from this. We've increasingly moved from multispectral measurements to hyperspectral measurements, from 10 bands to 200 bands. To achieve that, we use diffraction gratings. So some of you will have picked up a compact disc, right? You flip it over and you get this rainbow of colors, right? That's because the grooves in the surface are about the same wavelength as visible light. And white light comes in, and these are the grooves in the surface, and then this is called, imagine it's just called the grating equation. And you can see that in here I've got a few variables, let's ignore m, but I've got lambda, which is the wavelength of the light. I've got d, which is the distance between the grooves. And then I've got a couple of angles here, which is the incidence angle and the exitance angle. So again, I can tune the surface of this grating to scatter light at different wavelengths over different angles. And in that way, if I'm interested in measuring this wavelength of light, I just put a detector here. Right? A different wavelength, the light will be bounced off in a different direction, and I put a detector here. A different wavelength, the light will be, lambda will be different, the angle of emergence will be different, and I put a detector here. Right? So in that way, you can build just a grating-based spectrometer, and you just position the detectors in in the positions to measure the emerging rays, which are at different wavelengths, because this is a function of wavelength. Again, this is not, you don't get tested on this or anything, but this is just an overview of the kind of ways that you can split light and some background to how people have done it. The last one is interferometry, which we're not going to talk about because it isn't that common, but that's a way that you can decompose white light into its component frequencies. Practically what that means is this second resolution, which is the spectral resolution of the data. How many spectral bands, how wide are they, and are there any gaps between them? So we're going to be looking at these data next week. So the Landsat thematic mappers is the United States land surveying spacecraft. They launched the first one in 1972 and they're now up to version 10. Landsat makes measurements in 6 spectral bands between the visible blue and the shortwave infrared. And these Gaussians just represent the band pass, right? So the wavelength over which we get measurements of light. 1, 2, 3, 4, 5, 6. So we only have 6. And if you look at it, we have this big gap here, right? So Landsat doesn't make any measurements of the amount of light reflected from the Earth's surface at 1.2 microns, because it doesn't have a channel that makes that measurement. Nor does it make measurements at about 1.9 microns. The Hyperion, which was launched after Landsat, it doesn't make 6, it makes 220 spectral measurements between the same wavelength interval with no gaps. So we love this, right? Because this allows us to build these really detailed spectral reflectance curves. This much less so. So if we just look here, here are a few clay minerals. And what I've shown, the thin lines are the Hyperion resolution, right? So 220 samples between here and here means I get these really detailed curves, right, with all the peaks and troughs, because I make a very high spectral resolution measurement. Superimposed, I've just put the wave channels of Landsat, where I have 1, 2, 3, 4, 5, 6. Right, these grey bars are the bands of Landsat. So, if you were trying to fingerprint these minerals, would you rather have Hyperion or Landsat data?
Hyperion.
Rather have Hyperion, right? Apart from, not only do you get a dense curve, but what if in the future people discover something that says, oh, if we make measurements at 1.2 microns, then we can really distinguish these minerals, which we didn't care about before, but now we found they're a really important tracer of some planetary process. With Landsat, it doesn't matter because you never made the measurement. Whereas with Hyperion, you can go back and you can say, oh yeah, I can see that in the Hyperion data because I measured the full spectrum. Okay. So you prefer the Hyperion data to the Landsat data because the Hyperion data is high spectral resolution and it allows you to build higher fidelity spectral reflectance curves, right? Which is where all of the information is encoded. What's the ratio of 220 to 6?
Like 3 points.
3 point something. 3.
If I divide
36.
6, how many? How many 6s are in 220?
36.7.
36, right. So, instead of having 6, I have 220. So going back to this thing, the person that's designing the computer on the spacecraft, they're going to have to store not 6 channels, 6 of these maps, but 220 of these maps. And the person who's designing the comms system has to downlink all of that data to the ground. And then the person on the ground who's responsible for archiving this data until the end of time has to have 36 times as much disk storage space to actually keep all this stuff. Right? So again, these are things where the scientist always wants this. Right? They want that, not these dots. But there are these knock-on effects which are really real in terms of complexity and cost of the mission. So again, they have to defend that they need that. They can't just say they want it because it's nice. The other thing that's interesting, so this is really, think about it from that. Spectral resolution is how many bands do I have? 1, because the more bands is better, because I can resolve more higher fidelity spectral reflectance curves. And it's those curves that contain the chemical information about the thing I care about. Also gaps in between them, right? But then also spectral range. So if we look here, over this spectral range, Landsat TM has 6 and Hyperion has 220, right? So Hyperion is way better. But let's look here. So I've just blown this up. Landsat makes 6 measurements in this part of the spectrum, but it also makes 1 long-wave infrared measurement. Hyperion does not make any long-wave infrared measurements. So if you care about measuring in the thermal infrared, Hyperion is of no use to you whatsoever, right? Because it doesn't make any measurements in the thermal infrared, whereas Landsat does. So this thing about what is better spectral resolution, it's a few things. How many bands do I have? Are there any gaps? But also, does the sensor make measurements in the wavelength interval that I care about? Right. And again, this is a design thing. These detectors are uncooled. This detector is cooled. So when they're specifying Landsat, they said, oh yeah, I want a thermal infrared channel. The physicists and engineers are saying, well, I've got to make that band gap in my semiconductor really small because long-wave infrared photons don't have much energy. The whole spacecraft is radiating because it's above 0 Kelvin, which means I have to cool this detector cryogenically in order to beat down the noise and improve my signal. Which means now I have to fly a cryocooler, a small fridge on the spacecraft, which is power, vibration, it's a moving part, all that sort of stuff. And these reflectance spectrometers are really common now. So this is Chrism, and I've did I put it on? Okay, you can go and find all these spectra here if you go to this website. So Chrism was a European measurement, but you see again, remote sensing is curve held. So we have spectral reflectance, we have reflectance here against wavelength here, and here are just a whole bunch of spectra that were not from the. These are the lab spectra, and then these are the spectra derived from the Chrism instrument at about 18 years for this. So you can see this is the Chrism spectra, and then using that kind of run length encoding thing that I showed you a while ago, they went to a library and they found the best match. And that's how they fingerprinted what was on the ground at each of these pixels. So you see that curve, it's not the same as that, right? But it's pretty similar. And if you match those, you'll find there's a pretty good match just using that kind of elementary algorithm I showed you earlier. But people see how this is working. Library spectra on the bottom, measured spectra on the top. You go to the library, you found it, and in that way you can say, not that you care, jarosite, chlorite, so this is a salt, this is an iron, this is an iron, CO2 ice, this is an iron oxide, like in Hawaii, water ice, so you can distinguish different things on the surface of the planet, right? But only because you have the high spectral resolution, right? If we had 6 bands, we wouldn't be able to do a lot of this work. But 6 bands have cost. Sorry, tons of bands have cost. So we've gone through this, we're up to this point now. So we've been through this a lot, right? This is what a focal plane looks like, so that's a dime. So this is the photosensitive material, and then this is the ROIC, and then these are all the readouts, right, from all the channels. So it's about that big. These things are expensive, especially if you're having a new one made. We've gone through this before, how they work. And as I showed you, these are the solar panels at my house. And then this is all I'm measuring here, right? This is power. So this is what comes out of the N-phase inverter software. Time versus power. When I have lots of photons striking the panel, it generates lots of photoelectrons, and that sustains a current, which allows me to save a bit of money on my electricity bill. This is the cartoon of what the detectors look like. People are kind of happy with the detector stuff. You know, so there's a ton of stuff I don't understand about detectors, but basically this is how, fundamentally, how a large class of detector works. And this is what they look like. The detector around the top, this is the thing that's sensitive to the light, right? This is the ROIC. So this is where the bucket and the gate are, the transistor and the capacitor. You open it for the integration time, you allow photoelectrons to flow in, and then you read out how much current you accumulated in that integration time. Right? These are the Indian bumps, which link each pixel in the photosensitive material to its corresponding ROIC, its corresponding gate, bucket in the ROIC. Right? Radiation on the top, and then I've just put here mercury, cadmium, telluride. So this just comes from that thing. Certain chemistries of detectors give you band gaps which are sensitive to photons with particular wavelengths, frequencies, or energies. Right. And in this class of detector, this is a common one, mercury, cadmium, telluride. you vary the fractions of these three things in the alloy, and that moves the band gap, which means you can make your detector sensitive to some wavelengths or not others. People in the planetary community like to go out to the extreme long wave infrared part of the spectrum because interesting materials have interesting absorption features at really long wavelengths, like 30 microns, 25 microns. We don't do that on Earth because we don't see any of that light, because Earth's atmosphere is opaque to anything which is greater than 14 microns. Right? There's a huge carbon dioxide absorption feature. So on Earth, we don't design any detectors which are sensitive to light beyond 14 microns. Okay. In the planetary community, they are interested in doing that, and the way you do that is you increase the amount of mercury in the alloy. Right? People see mercury. What is mercury? What phase does it typically inhabit? It's a liquid, right? So if you increase the amount of mercury in this thing, eventually these things aren't like a solid crystal, they're more like a paste. And they're really, really hard to work with, and therefore really expensive to make. Let's just see how many we've got. Not too many, so bear with me. Right? Everybody ferociously bored? You look it. You bored?
Nah, I love talking about detectors.
Okay, so this gets back to your question about what the maps are. So you're going to look at these data. The radiance is measured and encoded as DM in a binary store. So this is the big island. You'll look at this image, I think, next week. So we have 185 kilometers on the side, Landsat 7 enhanced thematic mapper. Here we have a false color image. So these aren't real colors. They kind of look real colors, but they're not. What we're showing here is the amount of light reflected from the Earth's surface at 2 microns, displayed as red. The amount of light reflected from the Earth's surface at 1.6 microns, displayed as green. And the amount of light reflected from the Earth's surface in the visible red part of the spectrum as blue. Right? So if we just look at the image, if it's green in here, so this goes back to that, how do you interpret images, right? So I see a green pixel right here. So if I see vivid green, what does that mean?
It's reflection green.
It's absorbing, not green.
Right, so again, the way to express it is, I don't know which wavelengths are displayed in each color channel. However, I have a really strong signal in the green channel. Right? The next question is, what wavelengths do I have displayed in the green channel? Right? And I just told you it's that one, right? 1.6 microns. And in the red and blue, where I'm not getting signal, right, which means whatever wavelengths I'm measuring there and not getting much reflectance are 2.2 microns and about, in the visible red, about 0.7 microns. So that green color is not telling me that the ground is green, right? Even though it is, this is forest, right? But this is just a happy coincidence. What it's telling me is whatever is in these 30-meter pixels on this part of the ground is reflecting a lot of photons with a wavelength of 1.6 microns, but not reflecting a lot of photons with a wavelength of 2.2 or 0.65. And if it isn't reflecting a lot of photons with wavelengths of 2.2 or 0.65, that means it is absorbing those photons, right? So whatever is in these pixels is strongly absorbing photons in 2.2 and 0.65, right? And that absorption is the interesting thing, because there's something about the chemistry of whatever is on the ground where that material is just gobbling up photons at those wavelengths and therefore not reflecting. You get that? What does it look like? So this is just a zoom in, so the spatial resolution of this data is 30 meters, right? As I said before, for each band, for each of the 7 bands that we have for Landsat ETM Plus, we have 1 map per wave channel, right? So these are real data. For the band 7, these are the actual digital numbers, right? So these digital numbers correspond to the number of photons that had that energy reflected from each 30-meter patch of ground, right? And then the same for band 5, which is 1.6, and band 3, which is this. So if we don't break that chain, then I'll show you in a couple of slides. I can convert this to spectral radiance. So this is a number that's convenient for storage and transmission, but it's not a real number. Right? DN is not a real number. But I can convert this to spectral radiance in units of watts per meter squared per steradian per micron, which is a real number. You remember this is DN for storage, but I converted an analog representation of the photoelectrons that were generated into a digital representation, zeros and ones. The way we do that is, and this is just a picture, so we have 8 bits, base 2. I can store, with these 8 bits, I can store any number between 0 and 255. Right? So let's just show how I do that. If I turn this bit on, 1 not 0, and then I multiply it by 2 to the 7, I get 128. 2 to the 6, 64, 2 to the 5, 32, and so on until I get 2 to the 0, which is the 1. Right? Now if I turn all of these 8 bits on, and I generate these numbers and I add them together, I get 255. Right? If I make all these 0, I get 0. Right? I can turn these on and off in any combination, and I can store any number between 0 and 255. Right? So just an example here. If the number's 154, I turn this one on, these are off, this one on, this one on, this off, this on, this off, and I add those up and I get 154. Right? So that's how the digital number is related to this binary representation, which is the output of our AD processing. Right? When we're converting photoelectrons in current or volts or something to a binary representation, that's how I switch between the binary and the digital number. For 8-bit quantization. So this basically tells me when I'm looking at the surface of Mars and I'm looking at that patch of ground and that patch of ground, I can distinguish 256 different brightness levels. Right? What if that's not enough?
Use more bits.
Use more bits, right? I can add more bits. So this is kind of a low cost design change, right? There is some cost, but if I go from 8-bit to 16-bit, now what's my data range? You have to work it out. 16-bit is like, depends on whether it's signed or unsigned, but if it's signed, it's like minus 32,767 to plus 32,767, and then if it's not signed, it's 0 to about 65,000, right? So the difference between 8-bit and 16-bit is for 8-bit I can distinguish 256 different variations in brightness. For 16-bit I can distinguish 65,000 different levels of brightness, right? The cost is 1 extra bit, right? So there is a cost to whoever's designing the onboard computer storage and data handling, but it's not enormous. Now, the relevance of that is basically the precision and the measurement. So this other resolution, the radiometric resolution, is with what precision can we resolve differences in the light reflected, right? So if that patch of ground and that patch of ground, that pixel and that pixel are different in the amount of light they reflect, can I distinguish it, right? Do I make a precise enough measurement of DN in order to say this one is slightly brighter than that one, or is it lost in the noise of my sound? So if we just look here, 1-bit, 2-bit through 16-bit. The DN range for 1-bit is 0 and 1, so not very good. I end up with black and white images. 8-bit, 255, 4-bit, 15. If I go to 16-bit, I get all the way up here. But this picture just shows that if this is the minimum radius measurement by the instrument, and this is the maximum spectral radius measurement over here, I can distinguish up to 65,000 shades of grey versus 16, right? So this is more precise, right? I can detect really subtle changes in the amount of light reflected from that pixel and that pixel if I used 16-bit encoding rather than 8-bit encoding. And the way to think of it is it's just like a ruler, right? If I had a ruler and it was marked in inches, I could measure the length of this table with a precision of less than an inch, right? No more, no better than an inch. If it's marked off in eighths, I can do it more precisely. If it's marked off in 16ths, I can do it more precisely. That's basically just what you're seeing there. So radiometric resolution is how can I distinguish subtle variations in spectral radiance from different pixels, and the cost is just using an extra bit. So it's not a big deal. Right, 2 more. Do you mind if we get rid of these 2 slides?
Yeah,
Is that all right? So closing this loop down, you remember I had that loop, we had that chain, and we had those functional statements about how if we don't break the chain, then we can take the DN that you're going to get in class next week, and you can use it to work out the spectral radiance in each wave channel that came from each 30-meter patch of the ground, which is like doing science, right? Okay. So how does it work? For the Landsat data you're going to use, this is a picture of Mount Etna. a long time ago. This is a Landsat image of the summit of the mountain, so that's what that looked like from space at the time this activity was taking place. Now, I have a DN, right? So I go into this image in the same way you're going to do next week. I can say, well, in Landsat band 5, which is 2.22 microns, the DN from that pixel there was 205, right? But that doesn't mean anything, right, as we've said. But fortunately, this thing is calibrated. What I want to do is convert DN to spectral radiance. Right? I want to make sure I can take my DN and go all the way back to this number. Right? So the way I do it is I just apply an equation that either came from a website or came with the data, or in the old-fashioned days used to come in a peer-reviewed publication. This is the calibration of the Landsat spacecraft. So spectral radiance in watts per meter squared per radian per micron is found by taking the DN in Landsat band 5 and then subbing in Lmax and Lmin for Landsat band 5 minus 131. And if I just plug that in, 205 is the DN, 31 is Lmax for Landsat band 5. Lmin is not close to 1, it's just an offset. Divided by 255, add the offset again, I get 24.8 watts per meter squared per radian per micron. Right. If I went into this pixel or this pixel and this pixel and plucked out the digital number, I'll plug it in here. As long as I apply the right slope and offset, then I can generate the spectral radiance. Right. So and I've just put it up here, I've just plotted these things up for different DNs against radiances for all these different bands. And you see it's just the equation of a straight line, y equals mx plus c. An instrument that isn't calibrated is not an instrument. If all I get from it is DN, and I don't know how DN translates into spectral radiance, or I don't know how a change in DN from 255 to 254 translates into real numbers like spectral radiance, then I can't do any science with that instrument at all. So all instruments have to be calibrated. You can't do any science. Your camera's not calibrated, right? So you couldn't really do a whole lot of science with it. You could calibrate it, and the way you calibrate it is you do something like this. So this is over in the lab. I'll see if we can do something like this later in the semester. This thing's called an integrating sphere. So it just has a couple of lamps in there, which, if you like, simulates sunlight. And then it has a detector which measures the composition of the light in this thing. So I know when I turn these knobs, I can vary the intensity of the spectral radiance of the light, right, just by opening apertures that allow more light to flood in or less light. And I'm measuring it with this, right? So I know the spectral radiance in here. What I then do is I just put my instrument in front of this hole, right? And I turn my instrument on, and I turn the light down. I turn these knobs all the way to the right. It's pretty dark in this hole. And I point the instrument in and I say, well, I know the spectral radiance in here is this number, right, less than 1. What's the DN that the instrument is telling me? And the DN is, I don't know, it's like here, that's 50. And I just plot. Okay. And then I turn the knob slightly to the left, and I admit more light into the sphere. And it goes up. And then I say, well, now what's the DN? And the DN should go up, right? Because more photons are arriving at the focal plane array. That means more photoelectrons are being generated. That means the DN should go up, right? And I put another plot, and then I just keep doing that. I just keep emitting more and more light into the sphere, known amounts of light, and then I just keep recording the DN that the instrument's giving me. And at the end of it, I go from here to here, and I fit a straight line, and that allows me to generate a calibration coefficient for that wavelength. And then to do the other wavelength, there are a couple of ways I can do it. I could put a filter in here, or I could put a filter on the instrument itself, and then I could reproduce that measurement for a different wavelength and produce another regression equation that allows me to calibrate from DN to spectral radiance. But that's how easy that is. It's much just calibration. Okay, done for today. Are you hanging around to see Peter now or something? You're done. Right, so sorry about that. We went on for ages.
Another class.
Right. So you've got the PowerPoint. We'll meet again next time. So have a read of it, and then If anybody have any pressing questions, come back and we can talk about them before class on Thursday. If not, we'll move on to something else.